Every night, without pause, without announcement, small fragments of ancient comets enter Earth's atmosphere. They arrive as they have for billions of years, tiny particles no larger than grains of sand, moving at speeds that would carry them from New York to Los Angeles in less than 2 minutes. Most of them weigh less than 1 gram. Many weigh far less than that. Yet each one, in its final moments, produces a brief flash of light bright enough to be visible from the ground more than 80 kilometers below. This happens constantly, not occasionally, not during special events, constantly. Scientists estimate that approximately 48.5 tons of this material enters Earth's atmosphere every single day. That number represents the combined mass of roughly 70 adult human beings, but distributed across countless individual particles, each following its own trajectory, each originating from a different point along some ancient comet's orbital path. The vast majority of this material vaporizes completely before reaching 10 kilometers above the surface. It becomes part of the atmosphere itself, adding microscopic quantities of iron, magnesium, sodium, and other elements to the thin layers of air where meteors burn. Right now, even in full daylight, meteoroids are entering the atmosphere. You cannot see them because the sun's light overwhelms their brief glow, but they are there. Radar installations around the world detect them every hour of every day, tracking their ionization trails, measuring their velocities, recording their radiance. The atmosphere never stops catching these particles. Earth's orbital motion never stops carrying us through the scattered remnants of comets that passed through the inner solar system decades, centuries, or millennia ago. When Earth's orbit happens to intersect a particularly dense concentration of this debris, we call it a meteor shower. The name suggests something dramatic, but the reality is quieter than most people imagine. Even during a strong shower, you might see 1 meteor per minute if conditions are ideal. During a typical shower, the rate drops to perhaps 10 or 15 per hour. These are not sudden bursts. They are gradual increases in what is already a constant background phenomenon. The particles themselves have been waiting for this encounter for a very long time. A meteoroid that produces a visible meteor tonight might have been released from its parent comet during a pass through the inner solar system in the year 1862 or 1750 or even longer ago. Some of the dust currently in the Perseid stream was shed by Comet Swift-Tuttle during orbital passages that occurred when the Roman Empire was young. The particles have been slowly spreading along the comet's orbital path ever since, nudged by the gentle pressure of sunlight, pulled slightly by the gravity of planets, gradually dispersing into a long, diffuse cloud that Earth encounters once each year. These streams of debris are not uniform. They have structure, texture, variation in density. Some regions contain material from the comet's most recent passage. Other regions hold dust that was released thousands of years ago. When Earth passes through a denser filament within the stream, the meteor rate increases. When we pass through a thinner region, the rate decreases. The entire stream is moving through space together, following approximately the same orbit as its parent comet, a river of particles flowing endlessly around the sun. You are moving through space right now. Your velocity relative to the sun is approximately 30 kilometers per second, just by virtue of being on Earth's surface. That speed carries you through one Earth orbit every 365.25 days, along a path that intersects various comet debris streams at predictable times each year. The motion is smooth, continuous, imperceptible to your senses. You cannot feel it any more than you can feel the rotation of Earth itself. But it is real, and it is this motion that brings you into contact with ancient cometary dust. When a particle from one of these streams encounters Earth's atmosphere, it does so at a combined velocity that depends on both Earth's orbital speed and the particle's own velocity. For particles in prograde orbits, moving in the same general direction as Earth, the encounter speeds are lower, perhaps 27 kilometers per second for the torids. For particles in retrograde orbits, moving opposite to Earth's direction, the encounter speeds can reach 71 kilometers per second, as happens with the Leonids. That is 71,000 meters per second. At that speed, the meteoroid crosses the entire thickness of the atmosphere's densest layers in less than 2 seconds. We will explore these encounters in detail as this journey continues. We will examine the physics of atmospheric entry, the chemistry of ionized trails, the geometry that creates the illusion of a radiant point. We will look at historical observations spanning thousands of years, at the mathematics that allows us to predict shower activity, at the specific characteristics of the major annual showers. We will consider the particles themselves, their sizes, their compositions, their origins in the volatile ices of distant cometary nuclei. This will not be a hurried exploration. There is no rush to reach any particular destination, no climax to build toward, no dramatic revelation waiting at the end. The information will unfold gradually, calmly, with attention to detail and accuracy. Each section will develop naturally from the previous one, maintaining a steady rhythm, a consistent tone of quiet investigation. If you feel your attention drifting, that is perfectly acceptable. If you find yourself becoming drowsy, that is also fine. The purpose here is not to demand your focus, but to provide a gentle backdrop of factual information grounded in verified scientific understanding presented in a way that supports rest rather than demanding engagement. You can listen actively, or you can let the words wash over you as you drift towards sleep. Either approach is welcome. What matters is that the information itself remains accurate, remains calm, remains anchored in the reality of what meteor showers actually are and how they actually work. We are not here to dramatize or sensationalize. We are here to examine these phenomena with clarity and care, to understand them through patient observation and measured explanation. So settle in. Find a comfortable position. Let your breathing slow naturally. Allow your thoughts to quiet. We have a long journey ahead, one that will take us from the basic framework of meteor showers through progressively deeper layers of understanding, always maintaining this same steady pace, this same gentle approach to complex information. The meteors are falling now, as they always are. Let us begin to understand what that actually means. The journey we are about to take together will move through several distinct phases of understanding, each building naturally on what came before. We will start with the most fundamental concepts and gradually expand into greater detail and nuance. At no point will the pace become hurried or the tone shift toward urgency. Everything will unfold in its own time, with room for the information to settle, with space for your mind to process, or simply to rest. First, we will establish the basic framework. What is a meteor shower in the most literal, physical sense? What are the actual objects involved? Where do they come from, and why do they appear when and where they do? These foundational questions deserve clear, direct answers, presented without unnecessary complication. Once that foundation is secure, we can build upon it. From there, we will explore the mechanics of how comet debris spreads along orbital paths. This involves understanding how comets shed material, how that material disperses over time, how gravitational perturbations from planets gradually spread the debris into wide streams. The physics here is elegant in its simplicity, even though the full mathematical treatment would be complex. We will focus on the concepts rather than the equations, on the intuitive understanding rather than the rigorous derivation. Next comes the physics of atmospheric entry. When a particle traveling at dozens of kilometers per second encounters the first wisps of Earth's upper atmosphere, what happens? How does the air respond? Why does the encounter produce light? What determines the altitude at which the meteor becomes visible and the altitude at which it either completely vaporizes or finally slows enough that the glowing stops? These are questions with clear answers, grounded in thermodynamics and fluid mechanics and plasma physics, but we can approach them in ways that emphasize understanding over calculation. Approximately halfway through our journey, we will pause to reconsider the particles themselves from a different perspective. We have been treating them as abstract points moving through space, but they are actual physical objects with specific sizes, specific masses, specific compositions. A sand grain-sized meteoroid weighing 1/10 of a gram behaves differently from a pea-sized meteoroid weighing 2 grams. Both produce visible meteors, but the details differ. Understanding these differences helps us appreciate why meteor showers vary in their characteristics. Later sections will examine the chemistry of meteor trains, those glowing trails that sometimes persist for seconds or even minutes after the meteor itself has passed. We will look at the historical record of meteor observations across different cultures and time periods. We will consider the mathematics of meteor rates and the factors that influence what observers actually see. Each of these topics deserves careful attention, and each will receive it. As we move into the final portions of this exploration, the introduction of new dense information will gradually decrease. We will begin to revisit earlier concepts from slightly different angles, consolidating understanding, reinforcing the connections between different aspects of the phenomenon. The pace will remain steady, but the cognitive demand will gently lessen, allowing space for reflection or for sleep, whichever comes naturally. Throughout all of this, certain principles will remain constant. Every factual claim will be verifiable. Every number will be either directly sourced from scientific literature or clearly identified as an approximation. Any speculation about processes that are not yet fully understood will be clearly labeled as such. The tone will stay calm and measured. The pacing will stay consistent. The focus will stay on clarity rather than drama. You do not need to remember everything you hear. You do not need to remember anything at all. Really, the information is here for you to absorb at whatever level feels right, with whatever degree of attention you choose to bring to it. Some listeners will follow every detail actively. Others will drift in and out, catching fragments, letting the overall flow carry them toward rest. Both approaches are equally valid. What matters is that the experience remains gentle, remains grounded, remains true to the actual nature of these phenomena. Meteor showers are not supernatural events or dramatic cosmic spectacles requiring breathless narration. They are natural consequences of orbital mechanics and comet behavior and atmospheric physics, playing out on timescales ranging from fractions of a second to millions of years. They deserve to be described accurately, respectfully, with attention to detail, but without artificial excitement. So that is what we will do. We will maintain this steady rhythm, this quiet exploration, this commitment to factual accuracy and measured delivery. We will build understanding layer by layer, always giving you room to process, always giving you room to rest, always treating the material with the seriousness it deserves while keeping the tone peaceful and supportive. The next section will begin our detailed examination of what meteor showers actually are at the most fundamental level. Take a moment if you need it. Adjust your position. Let your eyes close if that feels comfortable. When you are ready, or when sleep begins to take you, we will continue forward together. To understand meteor showers, we must first understand three separate components and how they interact. These components are comets, meteoroids, and Earth's atmosphere. Each has specific characteristics that determine the nature of the phenomenon we observe. Comets are icy bodies that orbit the Sun in highly elliptical paths. Most comets spend the majority of their orbital periods in the cold outer regions of the solar system, far beyond the orbit of Mars, where temperatures are low enough that water ice, frozen carbon dioxide, frozen methane, and other volatile compounds remain stable. When a comet's orbit brings it closer to the Sun, solar radiation begins to warm its surface. The volatile ices sublime directly from solid to gas, bypassing the liquid phase entirely. This sublimation creates the characteristic coma and tail that make comets visually distinctive, but more importantly for our purposes, it releases embedded dust and rock particles. The process is not explosive or sudden. A comet does not shed all its material at once. Instead, each time it passes through the inner solar system, which might happen every few years or every few centuries, depending on its specific orbit, it loses a small fraction of its total mass. The subliming gases drag embedded particles along with them, carrying them away from the nucleus and into space. These particles, ranging in size from microscopic dust grains to pebble-sized chunks, are left behind along the comet's orbital path. Comet Swift-Tuttle, parent of the Perseid meteor shower, has an orbital period of approximately 133 years. Every time it completes one orbit and passes through the inner solar system again, it releases more material. Over many orbits spanning thousands of years, this process creates a continuous stream of debris distributed along the entire orbital path. The youngest material, released during the most recent passage, is still relatively concentrated near the comet itself. Older material has had more time to spread out, creating a broader, more diffuse distribution. This debris does not remain stationary in space. Each particle follows its own independent orbit around the Sun, an orbit that is very similar to, but not exactly identical to, the orbit of the parent comet. Tiny differences in the initial velocity at which particles were ejected, combined with the gentle effects of solar radiation pressure and gravitational perturbations from planets, cause the particles to gradually spread out along and around the comet's path. The result is what we call a meteoroid stream, a vast, diffuse cloud of particles following closely related orbits. Earth orbits the Sun once per year in a path that is nearly, but not perfectly circular. As Earth moves along this path, it occasionally intersects the orbits of various meteoroid streams. Because Earth's orbit is predictable, and because the meteoroid streams follow their own predictable orbits, these intersections occur at roughly the same time each year. Earth encounters the Perseid stream every August. Earth encounters the Geminid stream every December. Earth encounters the Leonid stream every November. The timing varies slightly from year to year, shifting by a day or so depending on exactly where Earth is in its orbit and how the gravitational influences of other planets have affected the positions of the various streams, but the basic pattern remains consistent. When Earth's orbit carries us into a meteoroid stream, the particles in that stream begin to encounter Earth's atmosphere. From our perspective on Earth's surface, the particles appear to be falling toward us, but that is not quite accurate. The particles are not targeting Earth or moving toward it deliberately. They are simply following their own orbits around the Sun. Earth happens to move into their path. The encounter is a consequence of orbital geometry, not of any attraction or targeting. The particles enter the atmosphere at the combined velocity of their own orbital motion and Earth's orbital motion. Earth moves around the Sun at approximately 29.6 kilometers per second. A meteoroid in the Perseid stream moves at a different velocity in a somewhat different direction. When the paths intersect, the relative velocity, the speed at which the meteoroid approaches through the atmosphere, depends on the angle and direction of the encounter. For the Perseids, this works out to approximately 59 kilometers per second. For the Leonids, it reaches 71 kilometers per second. For the Taurids, it drops to 27 kilometers per second. These velocities are extraordinarily high by any terrestrial standard. 59 kilometers per second is roughly 132,000 miles per hour. At that speed, a meteoroid crosses from the top of the atmosphere at an altitude of 100 kilometers down to an altitude of 80 kilometers in about 1/3 of a second. During that brief interval, it encounters rapidly increasing atmospheric density. At altitudes above 100 kilometers, the atmosphere is extremely thin. The density at 120 kilometers is approximately 1/10 billionth of the density at sea level. At this altitude, there are so few air molecules that a meteoroid experiences almost no resistance. It continues at its original velocity, essentially undisturbed. But as it descends, the air becomes denser exponentially. By 90 kilometers altitude, the density has increased by a factor of roughly 100. By 80 kilometers, it has increased by another factor of 10 or more. The meteoroid begins to compress the air directly ahead of it. The air cannot move out of the way fast enough at these speeds. A shock wave forms, a discontinuity in pressure and temperature where the air transitions from its normal state to a compressed, heated state. The temperature behind this shock wave rises dramatically, reaching thousands of degrees Kelvin. This heating occurs in the air, not primarily in the meteoroid itself, although the meteoroid's surface certainly experiences extreme temperatures as well. The heated air begins to glow. The atoms and molecules in the shocked air become excited to higher energy states, and when they relax back to lower energy states, they emit photons. Different atomic species emit photons at different wavelengths, creating characteristic spectral signatures. Oxygen emits green light at 557.7 nanometers. Nitrogen emits various lines in the red and near-infrared. Metals ablated from the meteoroid's surface add their own emission lines. Sodium produces the familiar yellow doublet at 589 nanometers. Magnesium contributes blue-green emission. Iron produces numerous lines throughout the visible spectrum. This glowing region extends along the meteoroid's path, creating the visible streak we call a meteor. The length of this streak depends on the meteoroid's size and velocity, on the altitude at which it first produces enough light to be visible, and on the altitude at which it either completely vaporizes or slows enough that the heating stops producing sufficient light. A typical meteor visible to the naked eye might leave a trail 10 to 30 kilometers long, although from the ground, perspective effects make it appear much shorter. The meteoroid itself is losing mass rapidly through this process. The technical term is ablation. The surface material vaporizes directly, atom by atom and molecule by molecule, stripped away by the intense heat and by direct collisions with air molecules moving at hypersonic speeds relative to the meteoroid. A meteoroid entering the atmosphere with a mass of 1 gram might lose 99% of that mass during the visible portion of its flight, which might last 1 second or less. The remaining 1%, if it survives at all, would be a tiny fragment weighing 10 milligrams, far too small to produce any further visible light, now moving slowly enough that aerodynamic heating no longer occurs. Most meteoroids that produce visible meteors do not survive to reach the ground. They completely vaporize somewhere between 90 and 60 kilometers altitude. The atoms and molecules that compose them become part of the atmosphere, permanently absorbed into the thin layers of the mesosphere and lower thermosphere. Only the largest meteoroids, those with initial masses of many grams or kilograms, have any chance of surviving atmospheric entry. Such large objects are rare in meteor showers, where the typical particle mass is well under 1 gram. This is the basic mechanism of meteor production. A small particle from an ancient comet, following its own orbit around the Sun, encounters Earth's atmosphere at hypersonic velocity. The encounter produces compression heating in the air. The heated air glows. The meteoroid ablates away. Within 1 or 2 seconds, the process is complete. The particle that might have been traveling through space for centuries or millennia has been transformed into a brief flash of light and a small quantity of atoms distributed throughout the upper atmosphere. Now multiply this single event by thousands or tens of thousands, occurring over the course of several hours as Earth moves through the densest part of a meteoroid stream. That is a meteor shower. Not a single, dramatic moment, but a gradual increase in the background rate of meteors, sustained for hours or days as we pass through the stream, then gradually decreasing again as we exit the other side. The term shower might suggest something more concentrated, more intense. And occasionally, when conditions are particularly favorable, meteor rates can indeed be impressive. The Leonid meteor storms of 1833 and 1866 produced estimated rates of hundreds of thousands of meteors per hour, so many that observers described them as falling like snow. But such events are rare. They occur only when Earth passes through particularly dense filaments of debris, material that was ejected from the parent comet during a recent passage and has not yet dispersed widely. Most years, most showers produce more modest rates, measured in tens or occasionally a few hundred meteors per hour under ideal conditions. Under ideal conditions is an important qualifier. The quoted rate. For a meteor shower, called the zenithal hourly rate, or ZHR, represents the number of meteors a single observer would see under perfect circumstances. Perfectly dark skies with no light pollution, the shower's radiant point directly overhead at the zenith, the observer's eyes fully adapted to darkness, and no moon present to wash out fainter meteors. Such conditions are rarely achieved in practice. Real observed rates are almost always lower, sometimes dramatically so. But even at lower rates, the showers remain scientifically fascinating and aesthetically pleasing phenomena. Each meteor represents a tangible connection to an ancient comet, a small piece of the early solar system making its final journey. The constancy of the showers, their predictability, the fact that we can forecast with confidence when and where to look for them, reflects the underlying order of orbital mechanics, the same gravitational principles that govern planetary motion and stellar dynamics throughout the universe. This is what a meteor shower is at its most fundamental level. Cometary debris in Earth's atmosphere, moving at hypersonic speeds, producing brief flashes of light through compression heating and ablation. Simple in concept, rich in detail, governed by well-understood physics, yet still capable of inspiring wonder when you step outside on a clear August night and watch the Perseids streak across the sky above you. We have established the foundation. Now we can build upon it. The architecture of a meteoroid stream, the three-dimensional structure of the debris cloud that produces a meteor shower, deserves closer examination. These streams are not simple, thin lines of particles tracing out the comet's orbit. They are complex, extended structures with variations in density, with different regions containing material of different ages, with internal structures that reflect the history of the parent comet and the gravitational perturbations the stream has experienced since its formation. When a comet releases material, the particles do not leave the nucleus at precisely the same velocity or in precisely the same direction. Each particle receives a slightly different impulse from the subliming gases. Particles released from the sunlit side of the nucleus might be ejected with more energy than particles from the shadow side. Particles embedded near the surface might escape more easily than particles buried deeper within. These small differences in initial conditions lead to diverging trajectories. Additionally, once in space, the particles experience forces that the comet's nucleus itself does not experience as strongly. Solar radiation pressure, the physical momentum carried by sunlight, exerts force on small particles in proportion to their surface area divided by their mass. Smaller particles have larger surface area to mass ratios and experience stronger radiation pressure effects. This pressure acts like a gentle but persistent wind, pushing particles slightly outward from the sun, slightly modifying their orbits over time. Particles also experience the Poynting-Robertson effect, a subtle consequence of radiation pressure combined with the particle's orbital motion. As a particle orbits the sun, it experiences sunlight from a direction that is not quite radial due to aberration, similar to how rain falling vertically appears to come at an angle when you are moving forward through it. This effect causes the particle to gradually lose angular momentum, slowly spiraling inward toward the sun over very long time scales. For particles in the size range that produces visible meteors, this effect is small compared to radiation pressure, but it becomes significant for very small particles and over timescales of thousands to millions of years. Gravitational perturbations from planets also affect the stream. When the stream, or a portion of it, passes near Jupiter or Saturn, the giant planet's gravity can pull particles into slightly different orbits. These perturbations accumulate over many orbital periods, gradually spreading the stream and creating additional structure within it. Computer models of meteoroid stream evolution show that, after several thousand years, the original relatively compact release of material becomes a long, diffuse cloud with complex internal variations. The result is that a mature meteoroid stream, one that has been evolving for thousands of years, extends not just along the comet's orbit, but also has significant width perpendicular to the orbit. When Earth encounters such a stream, we pass through it gradually over the course of several days or even weeks. The meteor shower becomes active as Earth enters the stream, reaches peak activity when Earth passes through the densest region, and gradually declines as Earth exits the other side. The width of the stream determines the duration of the shower. Narrow streams, which tend to be younger and have not had as much time to disperse, produce showers that are active for only a few days. The quadrantid meteor shower, which peaks in early January, has a very sharp maximum lasting only a few hours, suggesting that its debris stream is quite narrow. This is consistent with the theory that the quadrantids originate from an asteroid or possibly a disrupted comet that broke apart relatively recently, perhaps only 500 to 1,000 years ago, and has not yet had time to spread widely. Broader streams produce showers with longer durations. The Perseid meteor shower is active from mid-July through late August, a period of more than a month, although the peak occurs over just a few days around August 12th. This extended duration reflects the fact that the Perseid stream is quite wide, with debris spread over a large volume of space. Earth takes weeks to pass completely through it, encountering lower densities of particles near the edges and higher densities near the center. The density variations within a stream can be quite pronounced. Meteoroid stream models predict and observations confirm that streams are not uniformly populated with particles. There are filaments of higher density where material released during specific passages of the parent comet remains somewhat concentrated. When Earth passes through one of these dense filaments, the meteor rate increases noticeably, sometimes producing minor outbursts even during years when no major storm is expected. The most dramatic example of such structure appears in the Leonid stream. Comet 55. P. Tempel-Tuttle orbits the Sun once every 33.3 years. Each time it passes through the inner solar system, it releases fresh material that forms a relatively dense cloud. This cloud gradually disperses, but computer simulations show that for several decades after each passage, the material remains somewhat concentrated in specific filaments along the orbit. When Earth passes through one of these fresh filaments, Leonid meteor rates can increase from the typical 15 meteors per hour to hundreds or even thousands per hour. This is what happened in 1833, in 1866, in 1966, and more recently in 1999 and 2001. The timing of these Leonid storms is predictable once you understand the structure of the stream. By modeling the ejection of particles from the comet during each pass and tracking how those particles evolve under gravitational perturbations and radiation pressure, astronomers can forecast when Earth will encounter which filament and therefore when enhanced activity is likely. This type of forecasting has become increasingly sophisticated over the past few decades, allowing prediction not just of whether enhanced activity will occur, but also of approximately when during the shower's active period the peak is likely to happen and how strong the rates might be. Similar modeling has been applied to other streams with varying degrees of success. The Perseid stream has been modeled extensively, and predictions for enhanced activity from specific dust trails have sometimes proven accurate. The Geminid stream, which originates not from a comet but from an object called 3200 Phaethon that behaves more like an asteroid, shows different characteristics that reflect its unusual parent body. Phaethon is classified as an asteroid, but it is in a highly eccentric orbit that brings it very close to the Sun, closer than any other named asteroid. At perihelion, its distance from the Sun is only 0.14 astronomical units, which puts it well within the orbit of Mercury. At this close distance, temperatures on the surface become hot enough that even non-volatile materials might sublimate or fracture due to thermal stress. This may be how Phaethon releases the particles that form the Geminid stream, not through sublimation of water ice as in typical comets, but through thermal fracturing or degradation of rock under extreme heating. The Geminid stream reflects this unusual origin. The particles in the Geminid stream appear to be denser and more durable than typical cometary particles, which are often described as having a fluffy or fragile structure. Geminid meteors tend to penetrate deeper into the atmosphere before completely ablating, consistent with denser, more cohesive particles. The stream itself is quite broad and produces a shower that is active for about 2 weeks, with peak activity around December 13th. Each major meteoroid stream has its own characteristics, its own history, its own structure. The Orionid and Eta Aquariid showers both originate from the same parent body, Comet 1 P Halley, but they represent different parts of Halley's orbit. Earth encounters the Eta Aquariids in early May and the Orionids in late October, as our orbital path crosses Halley's orbit at two different points. The debris is not uniformly distributed along Halley's orbit, so the two showers have different characteristics despite sharing a common source. The Taurid meteor showers, both the northern and southern Taurids, originate from Comet 2 P Encke. Encke has an unusually short orbital period of just 3.3 years, the shortest known period of any comet. It has been observed on many returns, and its orbit is well determined. The Taurid stream is very old and has spread into a broad, diffuse cloud that Earth encounters over an extended period from September through November. The Taurids are not known for high rates, typically producing only 5 to 10 meteors per hour at peak, but they are known for producing an unusually high proportion of bright meteors and fireballs, suggesting that the stream contains some larger particles than are typical in most streams. The ages of these streams vary considerably. The Perseid stream is probably several thousand years old. The Leonid stream may be tens of thousands of years old, although much of the currently active material was released more recently. The Quadrantid stream might be only a few hundred years old. Over time, streams continue to evolve. Collisions between particles within the stream, though rare, gradually break down larger particles into smaller ones. Radiation pressure continues to push smaller particles into slightly different orbits. Gravitational perturbations continue to spread the material. Eventually, over timescales of hundreds of thousands to millions of years, the stream disperses so completely that it becomes indistinguishable from the general background of sporadic meteoroids that enter the atmosphere continuously from all directions. This evolution from a compact release of material to a dispersed stream to eventual complete integration into the sporadic background represents the life cycle of a meteoroid stream. At any given time, streams exist at all stages of this evolution. Young, compact streams produce narrow, intense showers. Older, dispersed streams produce broader, more moderate showers. Ancient streams have faded entirely, leaving only sporadic meteors with no apparent shower association. The architecture is elegant in its complexity. Each stream is unique, shaped by its own history, its own orbital characteristics, its own interactions with planetary gravity and radiation pressure. Yet all streams follow the same basic evolutionary path, governed by the same physical principles. Understanding this architecture, this structure, helps us understand why different showers behave differently, why some are predictable and others variable, why some produce consistent rates year after year while others show dramatic fluctuations. It also reminds us of the timescales involved. The material in these streams is ancient. The parent comets themselves are probably billions of years old, having formed in the outer solar system during the earliest epochs of the planetary system. The debris we see, burning in the atmosphere tonight, was released from those comets perhaps centuries or millennia ago. It has been drifting through space ever since, following its designated orbital path with patient inevitability until finally intersecting with Earth's atmosphere on this particular night. The streams persist. They will be there next year when Earth completes another orbit and returns to the same point. They will be there in 100 years, though the internal structure might have changed slightly. They will continue to exist for thousands of years more, gradually dispersing, gradually fading, but remaining fundamentally recognizable as coherent structures following the paths laid out by their parent comets long ago. This persistence, this predictability, this connection to deep time scales is part of what makes meteor showers fascinating beyond their visual appeal. They are windows into the past, traces of ancient cometary passages, evidence of processes that have been operating continuously since before human civilization, since before human existence, since the solar system was young. And they will continue, patient and inevitable, long after we are gone. When a meteoroid traveling at 50 or 60 or 70 kilometers per second encounters the upper atmosphere, the physics that governs what happens next operates on multiple levels simultaneously. There is the macroscopic fluid dynamics of a supersonic object moving through gas. There is the molecular level physics of collisions between atoms and molecules. There is the thermodynamics of extreme heating. There is the plasma physics of ionization and radiation. All of these occur together in a cascading sequence that unfolds over the span of 1 or 2 seconds, transforming a small, solid particle into a diffuse cloud of atoms and ions and a brief flash of visible light. Let us consider each layer of this process with the detail it deserves while maintaining our calm, steady pace. The meteoroid, as it descends from altitudes of 120 or 130 kilometers, first encounters atmospheric densities too low to produce significant effects. At these altitudes, the mean free path of air molecules, the average distance a molecule travels between collisions with other molecules, is measured in meters or even tens of meters. The meteoroid, typically less than 1 centimeter in diameter, can pass through this rarefied air without encountering many molecules at all. The collisions that do occur transfer some momentum, but not enough to produce noticeable heating or deceleration. As the meteoroid continues to descend, atmospheric density increases exponentially. The density at 90 kilometers altitude is approximately 10 times greater than at 100 kilometers. The density at 80 kilometers is approximately 10 times greater than at 90 kilometers. This exponential increase means that the meteoroid transitions very rapidly from a regime where atmospheric effects are negligible to a regime where they dominate the behavior of the particle. The transition typically begins somewhere between 190 kilometers, depending on the meteoroid's size, velocity, and composition. At this altitude, the air density becomes high enough that the meteoroid begins to compress the air ahead of it. The compression occurs because air molecules cannot move out of the way fast enough to allow the meteoroid to pass unimpeded. The molecules in the meteoroid's path are struck by the advancing particle and pushed forward, creating a region of elevated pressure directly in front of the meteoroid. This compression creates a shock wave, a thin region, perhaps a few centimeters thick, where the properties of the air change discontinuously. On the upstream side of the shock wave, the air has its normal properties at that altitude: low pressure, low temperature, low density relative to sea level, but typical for that altitude. On the downstream side, immediately behind the shock, the air is compressed to perhaps 10 or 20 times its normal density, and the temperature rises dramatically. The temperature rise occurs because the kinetic energy of the supersonic flow is converted into thermal energy through the compression process. The exact temperature depends on the meteoroid's velocity and the shock geometry, but for typical meteor velocities, temperatures behind the shock can reach 5,000 to 10,000 Kelvin. This is hot enough to dissociate molecular nitrogen and oxygen into their atomic constituents. It is hot enough to ionize many of those atoms, stripping away electrons. The result is a plasma, a state of matter where electrons move freely rather than being bound to specific atoms. This plasma is what produces the visible light we associate with meteors. The energy levels of atoms and ions in the plasma are elevated. When an electron transitions from a higher energy level to a lower one, it emits a photon. Different transitions produce photons of different energies, which correspond to different wavelengths of light. Oxygen atoms transitioning from certain excited states produce green light at 557.7 nanometers. This is often the dominant color in the brightest portions of a meteor's trail. Nitrogen, present in the atmosphere at about 78% concentration, contributes numerous emission lines throughout the visible and near-infrared spectrum. Molecular nitrogen ions produce a series of band emissions, particularly in the blue and violet regions of the spectrum. Atomic nitrogen produces red and near-infrared lines. The specific pattern of nitrogen emission depends on the temperature and the degree of ionization in the plasma. Metals ablated from the meteoroid surface add their own characteristic emissions. Sodium produces an intense yellow doublet at 589.0 and 589.6 nanometers. This sodium emission is often visible even in relatively faint meteors and can make the trail appear yellow or orange. Magnesium, present in significant quantities in many meteoroids, particularly those of cometary origin, produces blue and blue-green emission lines. Iron contributes many lines throughout the visible spectrum. Calcium, though less abundant than sodium or magnesium, produces distinctive red and violet lines. The detailed spectral analysis of meteor light reveals the composition of the meteoroid. By comparing the intensity of different emission lines, astronomers can determine the relative abundances of various elements in the particle. This has shown that most meteoroids in annual showers have compositions similar to carbonaceous chondrite meteorites, a type of primitive, carbon-rich rocky material thought to represent relatively unprocessed material from the early solar system. This is consistent with their origin in comets, which are also thought to preserve primitive solar system material. The ablation process, the actual loss of material from the meteoroid, occurs simultaneously with the plasma emission. The meteoroid's surface is heated both by direct collision with air molecules and by radiation from the hot plasma surrounding it. Surface temperatures can reach 2000 Kelvin or higher. At these temperatures, solid material sublimates directly to vapor, and the vapor immediately mixes with the surrounding plasma. The rate of ablation depends on several factors. Higher velocities produce more intense heating and therefore faster ablation. Larger meteoroids have lower surface area to mass ratios, which means they lose proportionally less mass per unit time than smaller particles. Denser meteoroids withstand ablation better than fragile, fluffy meteoroids. A dense, stony meteoroid might survive to lower altitudes than a porous, icy one entering at the same velocity. As the meteoroid ablates, it loses mass. This changes its momentum and therefore affects its deceleration rate. A lighter meteoroid slows down more easily than a heavier one when experiencing the same atmospheric drag force. This creates a feedback effect. As ablation proceeds and the meteoroid becomes lighter, it decelerates more rapidly, which reduces the heating, which can slow the ablation rate. For small meteoroids, this feedback leads to complete vaporization while the particle is still moving at several kilometers per second. For larger meteoroids, it can result in survival of a remnant fragment. The altitude at which a meteor becomes visible to observers on the ground depends primarily on two factors: the amount of light being produced and the darkness of the sky background. Under ideal conditions, with a dark, moonless sky and eyes fully adapted to darkness, a meteor, producing about a kilowatt of radiated power in the visible spectrum, becomes just detectable. This threshold corresponds roughly to meteors at magnitudes of about +6 on the astronomical magnitude scale, roughly the limit of naked eye visibility for stellar objects. For typical meteor velocities and meteoroid sizes, this visibility threshold is reached at altitudes around 100 to 110 kilometers. The meteor brightens as it descends, and the air density increases, reaching maximum brightness somewhere between 90 and 80 kilometers altitude. For most meteors, the trail then fades and disappears before the meteoroid reaches 60 kilometers altitude, either because the meteoroid has completely vaporized or because it has slowed below the velocity needed to produce sufficient heating. Brighter meteors, those approaching or exceeding the brightness of Venus or even the full moon, are called fireballs. These are produced by larger meteoroids, objects with initial masses of perhaps 10 grams or more. Fireballs penetrate deeper into the atmosphere, sometimes remaining visible down to altitudes of 30 or 40 kilometers. The brightest fireballs, called bolides, can be bright enough to cast shadows and may be visible in full daylight. These require even larger meteoroids, with masses of hundreds of grams to kilograms. For such large objects, ablation alone may not be sufficient to completely destroy the meteoroid during its atmospheric passage. A kilogram mass meteoroid entering the atmosphere might lose 90% of its mass to ablation, but still have 100 grams remaining when it slows to the point that ablation ceases. This remnant continues to decelerate under atmospheric drag, but no longer produces light. Eventually, it reaches terminal velocity, the speed at which aerodynamic drag exactly balances gravitational acceleration, and falls the remaining distance to the ground at a modest speed of perhaps 100 to 200 meters per second. Such objects are called meteorites, and they provide direct samples of solar system material that we can analyze in laboratories. However, meteorites are rare products of meteor shower activity. The vast majority of shower meteoroids are too small to survive atmospheric entry. Only the very largest particles, those at the tail end of the size distribution, have any chance of reaching the ground, and even then, survival is not guaranteed. Fragile, porous particles tend to break apart under the stresses of atmospheric entry, even if they are initially large enough that ablation would not completely destroy them. The physics of fragmentation is complex. A meteoroid experiencing rapid deceleration is subjected to enormous stresses. The front surface experiences higher air pressure than the back surface, creating a pressure gradient across the particle. If the meteoroid's material strength is insufficient to withstand this pressure difference, it breaks apart. Fragmentation can be sudden, with the meteoroid shattering into dozens or hundreds of pieces in a small fraction of a second, or it can be progressive, with small pieces flaking off continuously as the object descends. When sudden fragmentation occurs, it often produces a noticeable brightening of the meteor called a flare. The fragmentation exposes fresh surface area to the hot plasma, temporarily increasing the ablation rate and therefore the light output. Multiple flares along a meteor's path indicate multiple fragmentation events. Some meteors show half a dozen or more such flares, each marking a moment when the increasingly stressed remnant of the meteoroid finally gave way and broke into smaller pieces. The entire atmospheric entry process, from the altitude where the meteor first becomes visible to the altitude where it finally fades from view, typically covers 30 to 50 kilometers of altitude and occurs over 1 to 2 seconds. During this brief interval, a particle that might have been drifting through interplanetary space for thousands of years makes its final journey. The forces involved are enormous. The the heating is intense. The transformation is complete. And yet, to an observer on the ground, the event appears gentle, almost serene, a brief streak of light gliding silently across the stars. This apparent gentleness is an artifact of distance and perspective. If you could somehow be present in the upper atmosphere, just meters away from a meteor at the moment of its peak brightness, the experience would be dramatically different. The plasma temperature would be high enough to vaporize any material substance instantly. The shock wave, though thin, would carry enormous pressure. The light would be intense enough to cause immediate and permanent damage to unprotected eyes. The entire volume of air through which the meteoroid passes would be transformed into a glowing, ionized channel. But from the ground, 80 or 90 kilometers below, all of this fury and violence becomes a quiet, beautiful streak of light. Silent, because sound from that altitude takes several minutes to reach the surface, and has usually dissipated entirely long before arrival. The violence is contained, channeled, made aesthetically pleasing by the moderating effects of distance. This contrast between the physical reality of what is happening and the serene appearance from the observer's perspective is worth contemplating. It reminds us that perspective matters, that the same phenomenon can appear completely different when viewed from different vantage points, that what seems gentle and peaceful may involve processes of extraordinary intensity. The physics is clear. The mathematics is precise. The processes are understood in considerable detail, refined through decades of observation and modeling. Yet the beauty persists, undiminished by knowledge, perhaps even enhanced by the understanding of what is actually occurring in those brief moments when ancient dust becomes light. From any location on Earth's surface, meteors from an active shower appear to originate from a specific region of the sky. This region, called the radiant, is typically several degrees across, roughly circular or elliptical in shape, and positioned within or near a particular constellation. The Perseid shower's radiant is in Perseus. The Gemini shower's radiant is in Gemini. The Leonid shower's radiant is in Leo. This is not coincidental. It is a direct consequence of geometry and perspective, arising from the fact that meteoroids in a shower are traveling on nearly parallel paths when they encounter Earth's atmosphere. Consider what this means. Earth moves through a meteoroid stream, encountering thousands of particles distributed across a vast volume of space. These particles are not clustered tightly together. They are spread over distances of thousands or millions of kilometers. Yet they all follow very similar orbits because they all originated from the same parent comet and have been shaped by similar gravitational and radiation pressure forces during their evolution. When these particles enter Earth's atmosphere, they do so at nearly the same velocity and from nearly the same direction. The slight variations in their individual trajectories, the small differences in exactly where they intersect the atmosphere and at what precise angle, are usually too small to notice from the ground. What we observe is a collection of meteors that, despite occurring at different locations and different times throughout the night, all appear to be moving outward from the same point in the sky. This is a perspective effect, similar to the way that parallel railroad tracks appear to converge at a point on the horizon when you stand on the tracks and look into the distance. The tracks do not actually meet, they remain parallel. But from your perspective, they appear to converge because objects that are farther away occupy smaller angles in your field of view. Meteor trajectories work the same way. The meteoroids are moving on parallel paths through the atmosphere, but some of those paths are nearly aligned with your line of sight. You are looking almost directly along the path of the meteoroid as it approaches. These meteors appear to move very little across the sky. They start near the radiant and end near the radiant, creating short trails. Other paths are oriented more perpendicular to your line of sight. These meteors appear to move much farther across the sky, creating longer trails. But if you were to trace each trail backward, extending it in the opposite direction from its motion, all the paths would converge at the radiant point. The position of the radiant is determined by the direction from which the meteoroids are arriving. This direction, in turn, is determined by the orbital geometry of the meteoroid stream and Earth. For meteoroids in a particular stream, there is a specific velocity vector in space, a specific direction and speed at which they are moving relative to the Sun. Earth has its own velocity vector, its own direction and speed of orbital motion. The meteoroid's velocity relative to Earth is the vector difference between these two velocities. When you plot this relative velocity vector and extend it backward from Earth, the point where it intersects the celestial sphere, the imaginary sphere of the sky surrounding Earth, defines the radiant. For the Perseids, this point happens to lie in the constellation Perseus, so the shower is named after Perseus. For other showers, the radiant lies in different constellations, and the showers are named accordingly. The radiant is not a fixed point. As Earth rotates, the radiant appears to move across the sky just as the stars do, rising in the east, climbing to its highest point when it crosses the meridian, and setting in the west. Additionally, because Earth's orbital velocity changes direction as Earth moves along its orbit, and because the meteoroid stream has its own geometry, the radiant's position relative to the background stars also shifts slightly from day to day during the shower's active period. This is called the radiant drift. For most major showers, the radiant drifts eastward along the ecliptic at about 1 degree per day. This drift is small enough that the radiant remains within the same general region of sky throughout the shower's duration, but it is measurable and is taken into account when calculating precise radiant positions for specific dates. The size of the radiant, its angular diameter on the sky, reflects the dispersion of meteoroid velocities within the stream. If all meteoroids in a stream had exactly identical velocities, they would produce meteors that all appeared to converge at an infinitesimally small point. In reality, there is always some spread in velocities, some variation in the exact direction each meteoroid is traveling. This causes the trails, when traced backward, to converge not to a single point but to a small region, typically 2 to 5 degrees across for well-established showers. The practical implication for observers is that you do not need to stare directly at the radiant to see meteors. In fact, meteors near the radiant are often less impressive than those farther away because meteors near the radiant appear foreshortened, while meteors far from the radiant show their full length. The optimal observing strategy is usually to look about 45 degrees away from the radiant toward darker areas of the sky, while keeping the radiant somewhere within your peripheral vision. This strategy works because meteors can appear anywhere in the sky, but their apparent motion is always away from the radiant. If you are looking in a direction 45 degrees from the radiant, any meteor in your field of view will be traveling roughly perpendicular to your line of sight, maximizing its apparent length and making it easier to see. Meteors appearing in this zone are also more likely to be traveling through a longer path in the atmosphere, which can make them brighter. The radiant's altitude above the horizon also matters. When the radiant is low on the horizon, most of the meteoroid trajectories that would produce visible meteors are actually blocked by Earth itself. Only meteors approaching from nearly horizontal directions, grazing the top of the atmosphere, are visible. These grazing meteors can be spectacular when they occur, creating very long trails because the meteoroid travels a long distance through the atmosphere, but they are relatively rare. As the radiant rises higher in the sky, more and more of the meteoroid stream becomes accessible, and the meteor rate increases. For most showers, the radiant is highest in the sky during the pre-dawn hours. This is why meteor observing is often best between midnight and dawn. The combination of a high radiant and Earth's orbital motion carries you into the stream at the most favorable angle. Like driving into rain that is falling vertically, you hit more raindrops with the front of your car than with the back. Similarly, the side of Earth that is facing forward in Earth's orbital motion, which is the side experiencing pre-dawn hours, encounters more meteoroids than the side facing backward. There are exceptions. The Draconid meteor shower, which occurs in early October, is unusual in that its radiant is highest in the early evening rather than near dawn. This shower is also unusual in that it tends to produce more meteors when Earth is moving into the stream from behind rather than head-on, because the stream's orbit is retrograde relative to Earth's. The result is that peak Draconid activity often occurs soon after sunset, making it one of the few major showers that can be observed in the evening rather than requiring staying up until the early morning hours. Understanding the radiant and the geometry that creates it helps observers plan their sessions. If you know where the radiant will be and when, you can choose a location and a viewing direction that maximizes your chances of seeing meteors. You can also avoid wasting time looking at parts of the sky where meteors are unlikely to appear. More fundamentally, understanding the radiant helps us appreciate what we are actually seeing. Those streaks of light are not random. They are not sparks or bits of terrestrial debris or any of the other explanations that people proposed before the true nature of meteors was understood. They are particles from space, arriving from a specific direction at a specific velocity, burning up in the atmosphere according to precise physical laws. The fact that they all appear to radiate from a single point is not magic or mystery. It is perspective, it is geometry, it is a natural consequence of parallel motion viewed from a specific vantage point. This geometric understanding, this recognition that what appears to be divergence is actually parallelism, is satisfying in its elegance. The phenomenon is beautiful, not despite being explicable, but because the explanation reveals a deeper order, a harmony between appearance and reality that enriches rather than diminishes the aesthetic experience. When you stand outside during a meteor shower and watch the trails streak away from the radiant, you are witnessing a direct manifestation of orbital mechanics, of velocity vectors, of the relative motion of Earth and ancient cometary debris. You are seeing proof that the solar system operates according to consistent physical laws, that motion and trajectories can be predicted, that order underlies apparent randomness. This is the radiant, a perspective effect, a geometric construction, an illustration of parallelism, a named point in space that helps us organize and understand what we see. It is real in the sense that it marks a meaningful direction, the direction from which the meteoroids are arriving. It is illusory in the sense that no physical concentration of meteoroids exists at that location. The convergence exists in the geometry of perspective, not in the distribution of particles. Both aspects, the real and the illusory, are worth contemplating as you watch the meteors fall. We have reached approximately the midpoint of this exploration. It seems appropriate to pause here and reconsider the particles themselves, to shift our perspective from the large-scale geometry of streams and orbits to the much smaller scale of individual meteoroids. These are the actual objects that produce the phenomena we have been discussing. They are small, they are ancient, they are surprisingly varied in their properties despite their common origin. The size distribution of meteoroids in a typical shower stream spans several orders of magnitude. At the small end, particles less than 1/10 of a millimeter in diameter are present in vast numbers but contribute little to the visible meteor rate because they are too small to produce enough light to be visible. At the large end, centimeter-sized objects are rare but account for the brightest meteors, when they do occur. The bulk of visible meteors are produced by particles in the size range from roughly 1 millimeter to 1 centimeter, with masses ranging from perhaps 1/100th of a gram to a few grams. To put these sizes in perspective, 1 millimeter is about the diameter of a small grain of sand. 1 centimeter is about the diameter of a pea. Most of the meteors you see during a shower are produced by particles somewhere between these two extremes. The faintest meteors, those barely visible under dark skies, come from the sand grain-sized particles. The brighter meteors, those bright enough to get your attention even when you are not looking directly at them, come from particles a few millimeters across. The occasional brilliant meteor that lights up the landscape comes from a particle perhaps a centimeter or larger. The mass of a meteoroid depends not just on its size, but also on its density. Cometary meteoroids, which make up the majority of shower meteors, tend to have relatively low densities, typically around 500 to 1,000 kilograms per cubic meter. For comparison, solid rock has a density of about 3,000 kilograms per cubic meter, and water has a density of 1,000 kilograms per cubic meter. Cometary material is often described as having a structure similar to a dust ball, with solid grains weakly bound together by ices or organic compounds, leaving substantial pore space. This low density and porous structure affects how the meteoroid behaves during atmospheric entry. A porous particle has more surface area exposed to the hot plasma, which increases the ablation rate. It is also mechanically weaker and more prone to fragmentation. These factors mean that cometary meteoroids tend to ablate away completely at higher altitudes than denser, more cohesive objects would. The Geminid stream provides an interesting contrast. The parent body, 3,200 Phaethon, appears to be a rocky asteroid rather than an icy comet. The meteoroids in the Geminid stream reflect this origin. They have higher densities, perhaps 1,500 to 2,000 kilograms per cubic meter, and are more mechanically strong. Geminid meteors tend to penetrate deeper into the atmosphere before ablating completely, often remaining visible down to altitudes of 70 or even 60 kilometers compared to 80 to 90 kilometers for typical cometary meteors. The composition of meteoroids also varies, though all cometary particles share certain commonalities. They contain silicate minerals similar to those found in terrestrial rocks, olivine, pyroxene, and various other minerals formed at relatively low temperatures in the early solar system. They contain metallic grains, primarily iron and nickel, distributed throughout the material. They contain organic compounds, carbon-based molecules ranging from simple structures like polycyclic aromatic hydrocarbons to more complex chains and rings. And they contain, or originally contained, volatile ices, water ice, carbon dioxide ice, carbon monoxide ice, methane ice, ammonia ice, and other frozen compounds. By the time a meteoroid released from a comet reaches Earth's orbit, most of the more volatile ices have likely sublimated away. Water ice might remain if the particle has spent most of its existence far from the sun, but the more volatile compounds probably do not. What remains is primarily the rocky and organic material, with perhaps some residual water ice in the interior of larger particles. This composition is revealed through spectroscopic analysis of meteor light. The emission lines from sodium, magnesium, iron, calcium, and other elements provide direct evidence of the elemental composition. The relative intensities of these lines allow astronomers to estimate the abundances of different elements. Detailed studies have shown that meteor spectra generally match the composition of carbonaceous chondrite meteorites reasonably well, suggesting similar origin conditions and thermal histories. The number of meteoroids in a stream is difficult to determine directly, but can be estimated from the observed meteor rates and models of meteoroid detection. During a typical shower, producing a zenithal hourly rate of, say, 50 meteors, the number of meteoroids actually entering the atmosphere might be 1,000 times higher, because most meteoroids are too small or too faint to be visible to the naked eye. Radar observations, which can detect much fainter meteors than visual observations, confirm that the actual meteoroid flux is indeed much higher than the visual rate suggests. Integrating over the size distribution and accounting for detection limits, estimates suggest that during an active shower, Earth might be encountering meteoroids from that particular stream at a rate of several per second over the entire illuminated hemisphere. Most of these produce meteors too faint to see. A few produce the visible meteors that observers watch and count. The very rarest, the largest particles, produce the spectacular fireballs that occasionally surprise even experienced observers. The spatial distribution of these particles across the stream is not uniform. We have already discussed the large-scale structure of streams, the variations in density that create peaks and valleys in meteor rates as Earth passes through different regions. But there is also small-scale structure, clustering of particles on scales of tens or hundreds of kilometers that arises from the way particles were released from the comet and how they have evolved since. Computer simulations of meteoroid ejection from comet nuclei show that particles released at similar times and under similar conditions tend to remain clustered together for extended periods, sometimes for centuries after their release. This clustering is gradually eroded by differential orbital evolution. Slightly different velocities lead to gradually diverging trajectories, but it persists long enough to create noticeable effects in meteor observations. Observers sometimes report periods during a shower when meteors seem to arrive in bursts, with several occurring in quick succession, followed by quiet periods with no activity. These bursts might reflect passage through small-scale clusters of particles within the larger stream. Statistical analysis of meteor timing has found evidence for such clustering in several showers, though the effect is subtle and requires careful data collection to demonstrate convincingly. The age distribution of particles in a stream is also important. Fresh material, recently released from the comet during its most recent perihelion passage, has not yet had time to disperse widely. It remains relatively concentrated along the comet's orbital path and can produce enhanced meteor rates when Earth passes through it. Older material has dispersed more broadly, creating a more uniform background of activity throughout the shower's active period. For streams where the parent comet's orbit and ejection history are well known, models can predict which regions of the stream contain primarily fresh material and which contain older, more dispersed material. This allows prediction of outbursts and storms, as occurred with notable success for the Leonids in the late 1990s. Astronomers predicted that Earth would pass through dust trails released during specific historical passages of Comet Tempel-Tuttle, and those predictions were largely confirmed by subsequent observations showing enhanced activity at the predicted times. The lifetime of an individual meteoroid in a stream is finite but long. Small particles are removed relatively quickly by radiation pressure, which can push them into orbits that no longer intersect Earth's orbit. Larger particles remain in the stream for much longer periods. Collisions between meteoroids within the stream, though rare, can break particles into smaller pieces, gradually shifting the size distribution towards smaller sizes over time. The Poynting-Robertson effect causes slow orbital decay, particularly for smaller particles, eventually causing them to spiral into the Sun. Taken together, these effects mean that a meteoroid stream is not static. It is constantly evolving, constantly losing particles to various removal mechanisms, constantly being refreshed by new material from the parent comet if the comet is still active. The balance between these processes determines the long-term evolution and eventual dispersal of the stream. From a human perspective, these timescales are so long that they are effectively infinite. A meteor shower that exists today will exist in essentially the same form next year, and in 10 years, and in 100 years. Individual particles will be lost and replaced, but the overall structure persists. Only over thousands to tens of thousands of years do the changes become pronounced, enough to noticeably alter the shower's characteristics. This persistence across human timescales is part of what makes meteor showers valuable as astronomical phenomena. They are predictable. They are regular. They can be studied systematically, with confidence that observations made this year can be meaningfully compared to observations made decades ago or decades hence. This continuity enables long-term studies of stream evolution, refinement of orbital models, and testing of theoretical predictions about stream dynamics. It also means that the shower you observe tonight is, in all essential respects, the same shower that was observed by your grandparents and by people living centuries or millennia ago, and will be observed by people living centuries hence. The scale changes, the perspective differs, but the fundamental phenomenon remains constant. Ancient dust-meeting atmosphere, producing light, gradually dispersing into the background. The particles themselves are transient, existing as coherent objects for finite periods before being destroyed or lost. But the stream persists, the pattern persists, the phenomenon persists. In this way, meteor showers connect us to deep time, to processes operating on scales far longer than individual human lifespans, to the slow, patient evolution of the solar system itself. Returning your attention to those tiny particles, those grains of ancient dust, helps ground this understanding in physical reality. The abstractions of orbital mechanics and stream evolution ultimately reduce to countless small objects, each following its own trajectory, each with its own history, each destined to make one final, brilliant journey through Earth's atmosphere before ceasing to exist as an independent entity. It is humbling, in its way, to realize how small these objects are. It is also remarkable that such small objects can produce effects visible from dozens or hundreds of kilometers away, bright enough to catch your eye even when you are not expecting them, persistent enough to create memories that last long after the light itself has faded. Some meteors, particularly bright ones produced by larger or faster meteoroids, leave behind more than just a brief streak of light. They create persistent trains, glowing trails that can remain visible for seconds, minutes, or in rare cases, even an hour or more after the meteor itself has passed. These trains are not simply the continuation of the initial glow from the hot plasma. They represent a separate phenomenon, driven by different physical and chemical processes, revealing additional complexity in the interaction between meteoroids and the atmosphere. The initial flash of a meteor comes from the hot plasma created by shock heating as the meteoroid compresses the air in its path. This plasma contains ionized air molecules and atoms excited to high energy states, along with vaporized material from the meteoroid itself. The plasma glows brightly while it remains hot, but it cools rapidly, typically within a few seconds at most. The temperature drops from thousands of Kelvin to near the ambient atmospheric temperature of about 200 to 250 Kelvin. You would expect the glow to fade completely as the plasma cools, and it does fade dramatically. But sometimes, after the bright initial phase has ended, a fainter glow persists along the meteor's path. This is the persistent train. It has a different color, a different spectral character than the initial plasma emission. It often appears greenish or yellowish rather than white or bluish, and it can last far longer than any thermal emission could possibly persist at such low temperatures. The explanation involves atmospheric chemistry, specifically reactions involving atoms and molecules that were created or released during the meteor's passage, and that can participate in energy-releasing chemical reactions even at relatively low temperatures. One of the key reactions involves sodium atoms ablated from the meteoroid. The meteor deposits metallic sodium into the atmosphere at altitudes around 80 to 100 kilometers. This sodium can participate in a series of reactions that convert atmospheric ozone and atomic oxygen into molecular oxygen while regenerating the sodium. The reactions are: sodium atom reacts with ozone to form sodium monoxide and molecular oxygen. Sodium monoxide reacts with atomic oxygen to reform sodium atom and produce molecular oxygen. The net effect is the conversion of ozone and atomic oxygen into molecular oxygen, with sodium acting as a catalyst that is not consumed overall. Critically, the second reaction is sufficiently energetic that it can produce sodium atoms in an excited electronic state. When these excited sodium atoms relax to their ground state, they emit characteristic yellow light at 589 nanometers, the sodium D line. This emission can continue as long as sodium atoms remain in the trail and as long as ozone and atomic oxygen are available to react with them. Since the mixing of the meteor trail with surrounding air proceeds relatively slowly, this can maintain the emission for tens of seconds or even minutes after the meteor has passed. Similar processes involve other metallic atoms, particularly iron. Iron atoms can also participate in catalytic cycles that produce excited states and therefore emission. Iron oxide molecules, formed when iron atoms combine with atmospheric oxygen, have electronic transitions that produce orange and red emission in the 570 to 630 nanometer range. This FeO emission is often visible in persistent trains from iron-rich meteoroids. Magnesium follows similar chemistry, though the details differ. Magnesium atoms can react with ozone and atomic oxygen through cycles that produce excited magnesium atoms and molecules, leading to blue-green emission at 518 nanometers and other wavelengths. The relative importance of these different processes depends on the composition of the meteoroid and on the specific atmospheric conditions at the altitude where the train is located. Trains at higher altitudes, where atomic oxygen is more abundant, tend to show stronger sodium and iron emission. Trains at lower altitudes might show different chemistry as the relative abundances of atmospheric species change. The morphology of persistent trains is also interesting. They do not remain static. Winds in the upper atmosphere, which can reach speeds of 100 meters per second or more, distort and stretch the trains. A train that starts as a straight line along the meteor's path quickly becomes curved and twisted as different portions of it are carried by winds at different velocities. Wind shear, the variation in wind velocity with altitude and horizontal position, can create complex shapes, loops, spirals, knots. Observing these distortions provides information about wind patterns in the upper atmosphere at altitudes that are difficult to study by other means. The region around 90 to 100 kilometers altitude is too high for weather balloons and too low for satellites, making direct measurements challenging. Persistent meteor trains offer one of the few ways to probe wind structure in this regime. Not all bright meteors produce persistent trains. The phenomenon is more common with faster meteors, which deposit more energy and therefore create more dramatic chemical disruptions in the upper atmosphere. Leonid meteors, entering at 71 kilometers per second, produce persistent trains relatively frequently. Perseid meteors at 59 kilometers per second also produce them, though less often. Geminid meteors at 35 kilometers per second rarely produce persistent trains, presumably because the lower impact velocity does not create conditions conducive to the necessary chemistry. The composition of the meteoroid also matters. Meteoroids rich in sodium, magnesium, and iron are more likely to produce persistent trains than those with lower abundances of these metals. This compositional dependence can potentially be used to learn about the chemical makeup of different meteoroid streams by comparing the frequency and characteristics of persistent trains in different showers. Research on persistent trains has advanced significantly in recent decades through the use of wide-field video cameras and automated detection systems. These instruments can continuously monitor large portions of the sky, automatically detecting bright meteors and recording any subsequent trains. Analysis of thousands of such events has revealed that persistent trains are somewhat more common than earlier estimates suggested, occurring in perhaps 1 to 5% of bright meteors depending on the shower and observing conditions. The durations of persistent trains follow a roughly exponential distribution, with most lasting less than a minute but a significant minority persisting for several minutes. Trains lasting more than 10 minutes are rare but not unknown. The record, documented in photographs from the 1920s or 30s, is a train that reportedly remained visible for over an hour, though such extreme cases are exceptional. The chemistry of persistent trains connects to a broader set of questions about the role of meteoric material in atmospheric chemistry. The approximately 48 tons of meteoritic material entering the atmosphere each day becomes incorporated into the atmosphere at altitudes where it can influence various chemical processes. Some of this material eventually settles into the stratosphere, where it may contribute to the formation of aerosol layers or influence ozone chemistry. Some of it participates in the formation of noctilucent clouds, high-altitude clouds composed of ice crystals that form in the cold summer mesosphere at high latitudes. The meteoritic input is small compared to the total mass of the atmosphere, but it represents the primary source of certain trace metallic species at high altitudes. Understanding how these materials are deposited and how they subsequently evolve is an ongoing area of research, with implications for atmospheric models and for interpreting observations of the upper atmosphere. From an observational standpoint, persistent trains add an additional dimension of interest to meteor watching. The sudden appearance of a bright meteor is always attention-grabbing, but seeing a train develop and evolve over subsequent minutes adds a sense of continuation, a reminder that the event has consequences that play out over time. The train is not the meteor itself, but it is the meteor's legacy, a temporary but lasting mark on the atmosphere. This temporal extension, this persistence beyond the initial event, is thematically fitting. Meteor showers themselves are persistent phenomena, occurring reliably year after year. Individual meteors are brief, but the shower continues. Persistent trains operate on a middle time scale between these extremes, longer than an individual meteor, shorter than a shower, existing in the intermediate domain where chemical reactions and wind dispersal gradually erase what the meteor created. Watching a persistent train fade, slowly being stretched and distorted by high-altitude winds, eventually dissipating into invisibility, is a study in transience and transformation. What was a bright, well-defined line becomes a faint, curved structure, then fragments, then disappears. The atoms that created the glow are still there, now distributed more widely, chemically transformed, incorporated into the background atmosphere. But the distinctive pattern, the recognizable form, is gone. In this way, persistent trains mirror the larger pattern of meteor streams themselves. Structure exists. It persists for a while, it gradually disperses, eventually it becomes indistinguishable from background. The timescales differ enormously, minutes for trains, millennia for streams, but the fundamental pattern repeats across scales. This recognition of patterns repeating at different scales is satisfying in an intellectual sense. It suggests underlying unity in the processes, common principles operating across different regimes. It also serves as a reminder that persistence and transience are not opposites, but rather different phases of continuous processes. Nothing is truly permanent, but nothing disappears instantaneously either. Everything exists in states of transformation, moving from one configuration to another, temporarily maintaining recognizable forms before dissolving into new arrangements. The persistent train, then, is more than just an interesting visual phenomenon or a useful probe of upper atmosphere chemistry. It is also a metaphor, a concrete illustration of these abstract principles, playing out in real time in the night sky for anyone patient enough to watch and wait. Each year brings a succession of meteor showers, each with its own character, its own timing, its own observable features. Understanding these individual showers, their origins, their typical behaviors, and their variations helps observers know what to expect and helps scientists track the evolution of meteoroid streams over time. Let us examine the major annual showers in some detail, moving through the calendar year, noting their characteristics and the comets or asteroids from which they originate. The year begins with the quadrantids, peaking around January 3rd or 4th. This shower is notable for its very sharp maximum, with the highest rates lasting only a few hours. The zenithal hourly rate can reach 100 to 120 under ideal conditions, making it one of the strongest showers of the year when conditions align properly. However, the narrow peak means that observing from a particular location might miss the maximum if it occurs during daylight hours or when the radiant is below the horizon. The quadrantid radiant lies in the northern part of the constellation Bootes, near the border with Draco. The shower is named after Quadrans Muralis, an obsolete constellation that was once defined in this region but is no longer part of the official constellation list. The parent body is thought to be asteroid 2003 EH1, which may itself be a remnant of a larger comet that broke apart perhaps 500 to 1,000 years ago. The youth of this stream is consistent with its narrow structure and brief peak duration. Quadrantid meteors enter the atmosphere at about 41 kilometers per second, a moderate velocity compared to some other major showers. The meteors are typically faint, with mean apparent magnitudes around +3 to +6, meaning that most are visible only under reasonably dark skies. Observers in the northern hemisphere have a significant advantage for this shower because the radiant is located far north near the celestial pole, making it circumpolar from mid-northern latitudes. For observers in the southern hemisphere, the radiant never rises high enough for good viewing. Moving into spring, the Lyrid meteor shower becomes active in mid to late April, typically peaking around April 22nd. The Lyrids are one of the oldest known showers, with records of observations extending back to 687 BCE in ancient Chinese texts. This makes the Lyrids the oldest shower with a continuous historical record. The parent comet is C/1861 G1 Thatcher, which has an orbital period of approximately 415 years. Its most recent perihelion passage occurred in 1861, and it will not return until the 23rd century. The Lyrid zenithal hourly rate is typically around 18 meteors per hour, though occasional outbursts have been observed, with rates reaching 90 or more. The meteors are moderately fast, entering at 48 kilometers per second. The radiant is located near the bright star Vega in the constellation Lyra, making it easy to find for observers who can identify Vega. Like the quadrantids, the Lyrids favor northern hemisphere observers, though they are visible from moderate southern latitudes as well. In early May, the Eta Aquariid meteor shower reaches its peak, typically around May 5th or 6th. This shower, along with the Orionid shower in October, originates from Comet 1P Halley, perhaps the most famous comet known to astronomy. Halley orbits the Sun every 75 to 76 years, and Earth intersects its orbital path at 2 points, creating 2 separate showers from the same parent body. The debris is not uniformly distributed along Halley's orbit, so the 2 showers have different characteristics despite their common origin. The Eta Aquariids produce a zenithal hourly rate of about 50 meteors per hour at peak, though rates can vary considerably from year to year. The meteors are very fast, entering at 66 kilometers per second. This high velocity can produce meteors with persistent trains, and Eta Aquariid meteors are known for leaving brief ionization trails visible on radar. The radiant lies in the constellation Aquarius, which rises only a few hours before dawn from northern latitudes, limiting the observable period. Observers in the southern hemisphere have better viewing conditions because Aquarius rises earlier and reaches higher in the sky from southern latitudes. The Arietids, peaking in early June, present a special case. They are a daytime meteor shower. The radiant is located in the constellation Aries, which is in the same part of the sky as the Sun during early June. This means the radiant is above the horizon only during daylight hours, making the meteors invisible to optical observers. However, the Arietids can be detected using radiometeor observation techniques, where observers monitor the reflection of radio signals off the ionization trails created by meteors. Radio observations indicate that the Arietids may actually be one of the strongest annual showers, with zenithal hourly rates potentially exceeding 50, but optical confirmation is impossible due to the timing. Summer brings the southern delta Aquariids, peaking in late July, followed closely by the most famous shower of the year, the Perseids. The southern delta Aquariids produce a zenithal hourly rate of about 20 to 25 meteors per hour, with the radiant located in Aquarius. They are moderately fast meteors, entering at 41 kilometers per second. The parent body is thought to be Comet 96P Markholz, though this association is not as definitively established as for some other showers. These meteors are best viewed from the southern hemisphere, where Aquarius rises higher in the pre-dawn sky. The Perseids, peaking around August 12th, are arguably the most popular meteor shower for observers in the northern hemisphere. Several factors contribute to this popularity. First, the timing is excellent. Early to mid-August typically features warm weather in northern temperate regions, making overnight observing comfortable. Second, the zenithal hourly rate is consistently high, typically around 90 to 100 meteors per hour under ideal conditions. Third, the shower has a broad maximum, remaining active at elevated rates for several days around the peak, so observers are less dependent on precise timing than with showers like the quadrantids. Perseid meteors enter the atmosphere at 59 kilometers per second, making them fast, but not the fastest. They frequently produce bright meteors and fireballs, and they often leave persistent trains. The radiant is in Perseus, which rises in the northeast during evening hours and climbs steadily through the night, reaching good altitude in the hours before dawn. The parent comet is 109P Swift-Tuttle, which has an orbital period of 133 years. Its most recent perihelion was in 1992, and enhanced Perseid activity was observed in the years immediately following. The Perseids have been observed for at least 2,000 years, with possible references in ancient Roman and Chinese texts. The formal identification of the shower and its association with Comet Swift-Tuttle came in the 1860s, following the work of Giovanni Schiaparelli and others who were establishing the connection between comets and meteor showers. Fall begins with the Draconid meteor shower, sometimes called the Jacobinids, which peaks around October 8th. This shower is unusual in several respects. First, its radiant is in the constellation Draco, which is circumpolar from northern latitudes, meaning it is above the horizon all night. Second, the shower is typically more active in the evening hours rather than before dawn, contrary to most showers. Third, the shower's activity is highly variable, with most years producing only a few meteors per hour, but occasional outbursts producing hundreds or even thousands per hour. These outbursts tend to occur in years when the parent comet, 21P Jacobini Zinner, passes through perihelion. The comet has an orbital period of 6.6 years, and enhanced Draconid activity has been observed in multiple years following perihelion passages, including 1933, 1946, 1985, and 2011. The meteors are quite slow, entering at only 20 kilometers per second, the slowest of any major shower. The Orionid meteor shower, peaking around October 21st, is the second shower originating from Comet Halley. The zenithal hourly rate is typically around 20 to 25 meteors per hour, though, like the Eta Aquariids, this can vary considerably. Orionid meteors are very fast, entering at 66 kilometers per second, identical to the Eta Aquariids given their common parent. The radiant is located in Orion, specifically near the Club of Orion in traditional star chart depictions. Orion rises around midnight in October from mid-northern latitudes, providing good observing conditions in the hours before dawn. The Leonid meteor shower, peaking around November 17th, holds special significance in meteor astronomy due to its historical meteor storms. The parent comet, 55P Tempel-Tuttle, has an orbital period of 33.3 years. When Earth passes through relatively fresh debris trails, released during recent passages of the comet, Leonid rates can increase dramatically. The Great Leonid Storms of 1833 and 1866 produced estimated rates of 100,000 meteors per hour or more, with the sky reportedly filled with streaking meteors. More recently, enhanced activity occurred in 1999, 2000, 2001, and 2002, with peak rates reaching several thousand meteors per hour during the best displays. In non-storm years, the Leonid zenithal hourly rate is typically around 15 meteors per hour, respectable but not spectacular. The meteors are the fastest of any major shower, entering at 71 kilometers per second. This extreme velocity produces meteors that are often bright with persistent trains. The radiant is in Leo, rising around midnight in mid-November and reaching good altitude before dawn. Leonids are visible from both hemispheres, though northern observers have a slight advantage due to Leo's position relative to the celestial equator. The November to December time period also brings the Taurid meteor showers, both southern and northern Taurids. These are actually parts of a single extended stream associated with Comet 2P Encke. The stream is extremely broad, and Earth takes several weeks to pass through it, encountering the southern Taurids in early November and the northern Taurids in mid-November. The combined zenithal hourly rate is typically only 5 to 10 meteors per hour, among the lowest of the named showers. However, the Taurids have a reputation for producing an unusually high proportion of bright meteors and fireballs. The stream appears to contain a significant population of larger particles, which may relate to the stream's origin from the breakup of a larger body in the relatively recent past. Some researchers have suggested that asteroid 2004 TG10 and possibly other objects are fragments of this breakup, along with Comet Encke itself. Taurid meteors are quite slow, entering at 27 kilometers per second, the second slowest among major showers after the Draconids. Finally, December brings two strong showers nearly back-to-back. The Geminid meteor shower, peaking around December 13th or 14th, rivals the Perseids in reliability and intensity. The zenithal hourly rate typically reaches 120 to 150 meteors per hour under ideal conditions, making it numerically the strongest regular annual shower. Geminid meteors are moderately fast at 35 kilometers per second and tend to be bright and colorful, often showing green or yellow hues. The parent body, 3200 Phaethon, is an unusual object. It is classified as an asteroid but has an orbit that brings it very close to the Sun, closer than any other named asteroid. At perihelion, its distance from the Sun is only 0.14 astronomical units. This proximity to the Sun subjects Phaethon to extreme temperatures, perhaps sufficient to cause thermal fracturing and release of particles even without significant sublimation of ices. The Geminid stream's characteristics, including the relatively high density and durability of its particles, reflect this unusual origin. The Geminid radiant is in the constellation Gemini, which rises in the early evening in mid-December and remains well placed through much of the night. This makes the Geminids accessible to evening observers who do not wish to stay up until dawn, though rates increase as the radiant climbs higher later in the night. The shower is visible from both hemispheres and is increasingly recognized as one of the year's premier observing opportunities. The year closes with the Ursid meteor shower, peaking around December 22nd. This shower is often overlooked because it occurs just before Christmas when many people are occupied with holiday activities and because it typically produces only modest rates about 10 meteors per hour at peak. The parent comet is 8P Tuttle, which has an orbital period of 13.6 years. The radiant is near the star Kochab in Ursa Minor, the Little Dipper, positioned close to the north celestial pole. This makes the radiant circumpolar from northern latitudes, but invisible from the deep southern hemisphere. This tour through the years' major showers illustrates several themes. First, shower characteristics vary widely in terms of rates, meteor velocities, duration, and visibility from different locations. Second, most major showers originate from well-identified parent comets, with the notable exception of the Geminids. Third, timing and observing conditions matter enormously. A strong shower occurring during a full moon, or when its radiant is poorly placed, provides far less impressive viewing than a weaker shower occurring under optimal conditions. Fourth, historical observations spanning decades or centuries help establish the typical behavior of showers and identify unusual variations that might indicate encounters with fresh debris filaments or other special circumstances. For observers, this diversity means that every shower offers a somewhat different experience. The patient observer who follows showers through the year becomes familiar with these individual characteristics, learning which showers are reliably strong, which are variable, which produce mostly faint meteors, which generate impressive fireballs. This accumulated experience, built through many observing sessions across multiple years, develops an intuitive sense for what to expect and when. The predictability underlying this diversity is reassuring. You know that the Perseids will peak in mid-August. You know that the Geminids will be active in mid-December. You know that the Leonids might produce a storm, but probably will not in any given year. This knowledge allows planning, anticipation, preparation. You can mark your calendar, arrange your schedule, choose your observing location, and be confident that the meteors will appear when expected. This reliability, this fidelity to schedule, reflects the fundamental orderliness of orbital mechanics. The streams are where they are supposed to be. Earth passes through them when it is supposed to. The clockwork of gravity and motion operates with precision, year after year, century after century. Our ability to predict and observe meteor showers is a testament to the consistency of physical law and to our increasingly sophisticated understanding of how that law manifests in the movements of comets, meteoroids, and planets through space. The human observation of meteor showers extends far back into history, long before the scientific understanding of their nature was established. Ancient cultures across the world witnessed these celestial displays and interpreted them according to their own frameworks of understanding, often incorporating them into mythology, astrology, and religious beliefs. The records they left provide valuable data for modern astronomers, while also offering insight into how humans have perceived and made meaning from celestial phenomena across different eras and cultures. The oldest known written records of meteor showers come from East Asia, particularly from China, where systematic astronomical record-keeping was practiced for millennia. Chinese astronomers maintained detailed chronicles of celestial events, including comets, planetary positions, solar and lunar eclipses, and meteor showers. The earliest specific reference to what was probably a meteor shower appears in Chinese texts from 687 BCE, describing an event where the stars fell like rain. This description, repeated in various forms across different historical texts, became a common way of characterizing intense meteor activity. Later Chinese records provide more detailed descriptions of meteor showers, sometimes noting the date, the constellation from which the meteors appeared to radiate, the duration of the activity, and estimates of the number of meteors observed. These historical records have proven valuable for modern astronomers attempting to reconstruct the past activity of various meteoroid streams and to identify historical outbursts or storms that might not have been well documented elsewhere. Korean and Japanese astronomical records from the medieval period also contain numerous references to meteor showers and bright fireballs. These independent observations sometimes corroborate Chinese accounts, allowing modern researchers to confirm dates and characteristics of historical events. The consistency across these different sources strengthens confidence in the accuracy of the observations, despite the limitations of pre-modern observing techniques and the lack of standardized measurement protocols. In the Western tradition, ancient Greek and Roman texts occasionally mention what were probably meteors or meteor showers, though the descriptions are often less detailed than contemporary Asian records. The Greeks and Romans generally interpreted meteors as atmospheric phenomena, believing them to occur within Earth's atmosphere rather than being extraterrestrial in origin. This interpretation persisted in Western thought well into the early modern period. Greek and Roman writers often viewed comets and meteors as omens, signs of divine will or portents of significant earthly events. The appearance of a bright comet or an unusual meteor shower might be interpreted as foretelling the birth or death of a great leader, the outcome of a battle, or other momentous occurrences. This tendency to ascribe meaning to celestial phenomena reflected a worldview that saw Earth and the heavens as intimately connected, with events in the sky carrying significance for human affairs. One famous example comes from Roman historian Cassius Dio, who wrote about comet stars appearing after the death of Cleopatra in 30 BCE. Modern scholars have speculated that this might refer to the Perseid meteor shower, which occurs in August each year. The timing would be consistent with Cleopatra's death, and the plural comet stars might describe multiple meteors rather than a single comet. However, such interpretations must remain tentative given the limited detail in the historical account. The Middle Ages in Europe saw continued recording of celestial phenomena by monastery scholars and court astronomers. Medieval chronicles occasionally mention spectacular meteor displays, though again, the level of detail is often insufficient to identify specific showers with certainty. The interpretation remained primarily religious and astrological, with meteors seen as divine signs requiring interpretation by learned clergy. The scientific revolution of the 16th and 17th centuries began to change European perspectives on celestial phenomena. Astronomers like Tycho Brahe made careful positional measurements of comets, demonstrating that they must be located beyond the Moon and therefore could not be atmospheric phenomena as previously believed. This realization gradually extended to meteors as well, though the connection between comets and meteor showers would not be firmly established until the 19th century. The pivotal event in the modern understanding of meteor showers was the spectacular Leonid meteor storm of November 13, 1833. This event, visible across much of North America and parts of Europe, produced estimated rates of 100,000 meteors per hour at its peak. Contemporary accounts describe the sky as being filled with meteors, appearing to fall like snowflakes, so numerous that counting became impossible. The display lasted for several hours, from midnight until dawn, with the peak activity occurring in the hours before sunrise. The 1833 Leonids made an enormous impression on observers. Newspapers published numerous eyewitness accounts. Some observers interpreted the event in religious terms, seeing it as a sign of the end times. Others were simply awed by the spectacle. Critically, several scientifically minded observers, including Denison Olmsted, a professor at Yale University, recognized the event as an opportunity to gather systematic data. Olmsted published an appeal in newspapers asking people to report their observations, providing one of the first examples of crowdsourced scientific data collection. He received hundreds of responses from across the eastern United States. By analyzing these reports, Olmsted was able to determine that all the meteors appeared to radiate from a point in the constellation Leo, that the radiant maintained a fixed position relative to the background stars despite Earth's rotation, and that the activity occurred at essentially the same time for all observers, indicating a phenomenon centered on Earth rather than a local atmospheric effect. Olmsted's analysis, published in 1834, represented a major step toward understanding the true nature of meteor showers. He recognized that the meteors must be objects entering Earth's atmosphere from space and that they were following parallel paths, creating the radiant as a perspective effect. He also correctly predicted that the shower might recur, though he did not initially recognize the 33-year cycle that would become apparent after subsequent returns. The 1866 Leonid return confirmed the periodicity and allowed researchers to calculate the orbit of the meteor stream more precisely. In the same year, Italian astronomer Giovanni Schiaparelli made the crucial connection between meteor showers and comets, demonstrating that the Perseid meteor shower shared the same orbit as Comet Swift-Tuttle. Shortly thereafter, other researchers established the association between the Leonids and Comet Tempel-Tuttle. These connections firmly established that meteor showers are streams of debris left by comets and that the predictable recurrence of showers reflects the regular return of Earth to the same points in its orbit where these streams are encountered. The late 19th and early 20th centuries saw the systematic study of meteor showers expand considerably. Photography began to be used to record meteor trails, allowing precise measurement of positions and trajectories. Radio techniques, developed in the mid-20th century, allowed detection of meteors in daylight and during cloudy conditions, greatly expanding the range of observations. Radar meteor observations revealed the existence of daytime showers like the Arietids and provided detailed velocity measurements for meteors from various streams. The space age brought new observational capabilities. Spacecraft passing through meteoroid streams could detect impacts directly, providing data on the sizes and spatial distribution of particles too small to produce visible meteors. Infrared satellites could detect the glow from meteors too faint for ground-based observers. Computer modeling allowed simulation of meteoroid stream evolution, predicting when Earth might encounter dense filaments of fresh debris and forecasting potential outbursts or storms. The 1999 Leonid return provided a test of these predictive capabilities. Multiple research teams had calculated when Earth would pass through debris trails released during specific historical returns of Comet Tempel-Tuttle. The predictions proved largely accurate, with enhanced activity occurring at approximately the predicted times and rates. Observers and researchers deployed aircraft-mounted instruments to fly into the most favorable positions for observing the peak activity, and dedicated observers traveled to dark sky sites across multiple continents to document the event. The success of these predictions demonstrated how far understanding had advanced since Olmsted's initial analysis in 1834. Modern meteor science combines careful observation, detailed modeling of orbital evolution, and sophisticated analysis of both optical and radar data. The field has matured from descriptive astronomy into a quantitative science capable of making testable predictions and extracting information about the source regions and evolutionary histories of meteoroid streams. Yet despite all this progress, the fundamental experience of watching a meteor shower remains remarkably similar across the centuries. Whether you are an ancient Chinese astronomer recording the event in official chronicles, a farmer in 1833 watching the Leonid storm with wonder and perhaps trepidation, or a modern observer with cameras and computers documenting the Perseids, you are seeing the same basic phenomenon. Small particles of cosmic debris vaporizing in Earth's atmosphere, creating brief streaks of light against the background stars. The interpretations have changed. The understanding has deepened. The ability to predict and explain has improved immeasurably. But the visual experience, the aesthetic impact, the quiet drama of watching meteors arc across the sky remains constant across time and culture. This continuity is part of what makes meteor showers special. They connect us not just to the distant past of the solar system, but also to the human past, to countless other observers who have stood under the night sky and watched the same spectacle unfold. The historical record reminds us that scientific understanding is cumulative and progressive. Each generation builds on what came before, adding new observations, refining theories, developing better tools and techniques. The process is gradual but consistent. Questions that seemed unanswerable in one era become routine in the next. Phenomena that inspired awe and wonder retain their aesthetic appeal even as their physical basis becomes clear. This is the trajectory of human engagement with the natural world. From observation to understanding, from wonder to knowledge, from myth to science. And yet, the progression does not eliminate the wonder. It transforms it, deepens it, makes it more informed and more nuanced. Understanding that a meteor is a particle of ancient cometary debris traveling at 70 kilometers per second does not make it less beautiful. If anything, the knowledge enhances the experience, adding layers of meaning that earlier observers could not access. When you watch a meteor shower tonight, you participate in a tradition extending back thousands of years. You stand in a long line of observers, each contributing in their own way to the accumulated understanding of these phenomena. Your observation connects you to that history and to the slow, patient work of making sense of the cosmos through careful attention and systematic study. The rate at which meteors appear during a shower, the frequency with which you see them streak across the sky, is governed by several factors that interact in complex ways. Understanding these factors helps explain why meteor counts vary so much, depending on observing conditions, and why the quoted rates for meteor showers represent idealized values that are rarely achieved in practice. The foundational concept is the zenithal hourly rate, abbreviated ZHR. This represents the number of meteors a single observer would see per hour under very specific conditions. The showers radiant at the zenith, perfectly dark skies with a limiting magnitude of 6.5, and the observer's eyes fully adapted to darkness. The ZHR is a standardized measure that allows comparison between different showers and between different observation reports of the same shower. Actual observed rates are almost always lower than the ZHR, sometimes dramatically so. Each of the ideal conditions required for the ZHR represents something that is difficult to achieve in practice. Let us consider each factor individually. First, the radiance altitude. When the radiant is at the zenith, directly overhead, meteoroids from the shower can enter the atmosphere from all directions around that point, and all of them can potentially produce visible meteors. When the radiant is lower in the sky, say 45 degrees above the horizon, Some of the meteoroids that would have been visible with the radiant at the zenith are now approaching from below the horizon and cannot be seen because Earth blocks them. The fraction of meteors lost due to this geometric effect increases as the radiant drops lower. The mathematical relationship is approximately proportional to the sine A of the radiant's altitude angle. A radiant at 30 degrees altitude allows about 50% of the meteors that would be visible at the zenith. A radiant at 15 degrees altitude allows about 26%. A radiant right at the horizon allows essentially none, because all the meteoroids would be approaching from below and are blocked by Earth. For most showers, the radiant rises through the night, starting low in the evening and reaching its highest point near dawn. This is why meteor observing typically improves as the night progresses. Second, sky darkness. The ZHR assumes a limiting magnitude of 6.5, which corresponds to being able to see stars down to this faint level with the naked eye. This requires truly dark skies, far from city lights, with no moon present. Light pollution from artificial lights washes out fainter stars and fainter meteors. A sky with significant light pollution might have a limiting magnitude of 4 or even 3, meaning that stars fainter than this magnitude and meteors fainter than the corresponding meteor magnitude become invisible. Since faint meteors are much more numerous than bright meteors, losing the faint end of the distribution drastically reduces the observed rate. A shower with a ZHR of 100 meteors per hour might produce only 20 or 30 meteors per hour under suburban skies with moderate light pollution, and perhaps only 10 or fewer under urban skies with severe light pollution. The moon also affects this calculation. A full moon can raise the sky brightness to levels comparable to moderate light pollution, significantly reducing observed rates even from otherwise dark locations. Third, eye adaptation and observing technique. The ZHR assumes the observer's eyes are fully adapted to darkness, which takes about 20 to 30 minutes in complete darkness. Using a white light, even briefly, partially or completely, ruins this adaptation and reduces sensitivity to faint meteors. Proper technique involves remaining in darkness, using only dim red lights if illumination is necessary, and allowing sufficient time for full adaptation before beginning to count meteors seriously. Additionally, observer skill matters. Experienced observers tend to see more meteors than novices, partly because they know where to look and how to use their peripheral vision effectively, and partly because they have trained themselves to recognize meteors quickly even when not looking directly at them. The ZHR implicitly assumes a reasonably experienced observer. A complete novice might see significantly fewer meteors even under otherwise ideal conditions. Given these factors, calculating the expected observed rate for actual conditions requires corrections for each deviation from the ideal. The formula is observed rate equals ZHR times sine of radiant altitude times the correction factor for limiting magnitude. The limiting magnitude correction factor is empirical, derived from comparing actual observations under different conditions. A commonly used formula relates the correction factor to the ratio of the observed limiting magnitude to the reference limiting magnitude of 6.5. The exact form of this relationship is somewhat complex, but roughly speaking, each magnitude loss in limiting magnitude reduces the observed meteor rate by a factor of about 2 to 2.5. Applying these corrections allows prediction of what an observer should expect to see under specific conditions. For example, the Perseid meteor shower with a ZHR of 100, observed when the radiant is at 40 degrees altitude under skies with a limiting magnitude of 5.5, mild light pollution, or moonlight, would yield an expected rate of approximately 100 times sine of 40 degrees times the limiting magnitude correction for 5.5 versus 6.5 equals approximately 100 times 0.64 times 0.5, which equals about 32 meteors per hour. This is a substantial reduction from the nominal ZHR, illustrating why actual observed rates are often disappointing relative to quoted values. Observers seeing 30 meteors per hour during the Perseids might mistakenly think the shower is underperforming, when in fact the rate is entirely consistent with expectations given the observing conditions. Beyond these systematic factors, there is also intrinsic variation in the meteor rate itself. Meteoroid streams are not uniform in density. As Earth passes through the stream, it encounters regions of higher and lower density, causing the meteor rate to fluctuate over time. Observers sometimes report periods of enhanced activity, small outbursts where the rate temporarily increases by 50 or 100% for anywhere from a few minutes to an hour or more. These probably correspond to passage through denser filaments within the larger stream structure. The timing of the shower's peak also varies slightly from year to year, typically by a few hours, but occasionally more. Predictions for shower peaks are based on models of the stream's orbital evolution, and while these models are increasingly sophisticated, they are not perfect. An observer watching at the predicted peak time might actually be observing a few hours before or after the true maximum, resulting in lower rates than expected. Statistical fluctuation also plays a role. Even if the underlying meteor rate is constant, the times at which individual meteors appear are random. In any given hour, you might see more or fewer than the average rate simply due to chance. Over many hours, these fluctuations average out, but in a single hour or two of observing, they can be noticeable. Meteor counts follow Poisson statistics, which means the standard deviation of the count equals the square root of the expected count. An expected rate of 25 meteors per hour has a standard deviation of 5 meteors, so observed counts anywhere from 20 to 30 would be statistically unremarkable. For scientific analysis, meteor observations are typically reduced to standard conditions by applying corrections for all these factors, essentially working backward from the observed count to infer what the ZHR must have been. This allows combining observations from different observers at different locations observing under different conditions into a single coherent dataset. The International Meteor Organization maintains databases of such corrected observations, allowing study of how shower activity varies from year to year and making possible long-term studies of stream evolution. The mathematics underlying these corrections and the statistical analysis of meteor rates is well established but requires care to apply correctly. Observers contributing to scientific databases must record detailed information about their observing conditions. The times they observed, the center of their field of view, the limiting magnitude of their sky, and ideally the number of sporadic meteors, those not associated with any known shower, they observed, which helps calibrate their detection efficiency. This level of detail is unnecessary for casual observing, where the goal is simply enjoyment rather than scientific contribution. But understanding the factors that govern observed rates helps set realistic expectations and explains why the experience can vary so much depending on conditions. A strong shower under poor conditions might provide fewer meteors than a weak shower under excellent conditions. Timing matters, location matters, weather matters, moon phase matters. All these Factors interact to determine what you actually see. This complexity might seem frustrating, but it also means that improvement is possible. Finding darker skies dramatically improves the experience. Observing when the radiant is higher, usually in the hours before dawn, significantly increases the rate. Avoiding nights with bright moonlight or choosing to observe before the moon rises makes a substantial difference. These are factors within an observer's control, and exercising that control can transform a mediocre observing session into an excellent one. The predictability of meteor showers, combined with the understanding of what affects observed rates, empowers observers to plan effectively. You can check the moon phase for the night of a shower's peak. You can calculate when the radiant will be highest. You can research dark sky locations accessible from where you live. Armed with this information and understanding, you can maximize your chances of having a memorable observing experience. This is one of the pleasures of meteor observing. It rewards preparation and knowledge while remaining accessible to anyone willing to spend time under a dark sky. You do not need expensive equipment. You do not need specialized training. You need patience, dark skies, and willingness to spend hours gazing upward, waiting for the next streak of light to appear. The mathematics and the physics are interesting and informative, but ultimately, the core experience is simple and direct, watching cosmic dust become light. As we move toward the conclusion of this exploration, the introduction of new technical information begins to ease. We have covered the essential physics, the chemistry, the geometry, the historical context, and the observational considerations. What remains is to consolidate this understanding, to recognize the patterns that emerge across different aspects of the phenomenon, and to reflect on what meteor showers tell us about the broader cosmos. 1. Theme that has appeared repeatedly is continuity. Meteor showers are continuous phenomena operating across timescales from fractions of seconds to millions of years. In a fraction of a second, a meteoroid heats, ablates, and disappears, yet the process itself continues as the next meteoroid arrives and the next after that. Over hours and days, Earth passes through the meteoroid stream, the encounter persisting even as individual events come and go. Over years and decades, the shower recurs, predictable and reliable. Over centuries and millennia, the stream evolves, dispersing and spreading, yet maintaining coherence long enough to be recognizable across human history. This continuity reflects the underlying constancy of physical law. Gravity operates the same way today as it did 1,000,000 years ago and as it will 1,000,000 years hence. Orbital mechanics follows the same principles. Thermodynamics governs energy transfer in the same manner. The specifics change, the configurations evolve, but the rules remain fixed. Meteor showers are the result of these unchanging laws playing out in a specific configuration of comets, debris, and planetary orbits. Another recurring theme is the importance of perspective and scale. What appears violent from close-up appears serene from a distance. What happens in milliseconds from one viewpoint unfolds over minutes or hours from another. What seems like a single event at one scale reveals itself as a complex of many interconnected events at another scale. The meteoroid's perspective, if we could imagine such a thing, would be of sudden, catastrophic heating and destruction. Earth's perspective, considered globally, is of a gentle rain of particles adding infinitesimal amounts to the atmosphere's composition. The human observer's perspective is somewhere between close enough to see individual events, far enough to appreciate pattern and regularity. Scale also matters in understanding origins and evolution. The solar system is 4.6 billion years old. Comets are nearly as old, having formed in the earliest epochs of planetary formation. The debris streams we observe are typically thousands to tens of thousands of years old, recent in solar system terms, but ancient in human terms. The meteoroids currently burning in the atmosphere were released from their parent comets centuries or millennia ago. The light we see tonight represents the final moment of objects that have been drifting through space longer than recorded human history. This connection to deep time is humbling. It reminds us that we observe processes operating on scales vastly exceeding individual human experience, yet we can observe them, study them, and understand them. Science provides tools for transcending the limitations of human perception and timescale, allowing us to reconstruct histories extending far beyond living memory, and to predict futures extending far beyond individual lifespans. The meteor showers will continue, long after we are gone. The streams will persist, gradually dispersing over millennia, eventually fading into the sporadic background. New streams will form as other comets pass through the inner solar system and release their own debris. The process is ongoing, has always been ongoing, will continue to be ongoing. We are privileged to observe a particular snapshot of this continuous evolution, to see the current state of streams that formed in the past and that will evolve further in the future. This perspective can be sobering, confronting us with our own temporal limitations and insignificance in the grand scheme of cosmic timescales. It can also be liberating. The processes continue independent of human presence or attention. They do not require us. Yet we can observe them, appreciate them, find beauty and meaning in them. Our ability to understand, to make sense of patterns spanning millennia using observations collected over mere decades or centuries, represents a profound achievement of human intellect and cooperation. The international collaboration involved in modern meteor science exemplifies this cooperation. Observers from dozens of countries contribute data to shared databases. Researchers from different institutions work together on models and analysis. Results are published openly, subjected to peer review, refined through discussion and critique. This collective effort builds understanding incrementally, each contribution adding to the whole, each generation advancing further based on the work of previous generations. This cumulative, collaborative process is how science works at its best. No individual knows everything or can observe everything. But by combining many individual contributions, patterns emerge that no single observer could discern. The predicted timing of Leonid outbursts, for instance, requires modeling that incorporates observations spanning multiple apparitions of the parent comet, calculations of gravitational perturbations by planets, and detailed tracking of how debris ejection velocities map onto current spatial distributions. No individual could perform all this work alone, but a community of researchers, each contributing specialized expertise, can accomplish together what none could achieve individually. This distributed nature of scientific knowledge mirrors the distributed nature of meteoroid streams themselves. Just as individual meteoroids spread along the comet's orbit, each following its own slightly different trajectory, but collectively defining the stream, individual bits of knowledge and understanding, each contributed by different people at different times, spread through the scientific community and collectively define our understanding of these phenomena. The metaphor extends further. Just as meteoroid streams eventually disperse and fade, individual contributions to science are eventually absorbed into the background understanding, no longer cited explicitly, but incorporated into the foundation on which subsequent work builds. This is not a loss, but a transformation, a sign that the contribution has become part of the accepted framework. The pioneering work of Olmsted and Schiaparelli is no longer cited in every paper about meteor showers, not because it has become irrelevant, but because it has become foundational, assumed rather than argued for. Understanding this process, recognizing how knowledge accumulates and transforms over time, provides context for appreciating both the achievements of the past and the work of the present. Every observation, every calculation, every model contributes to the evolving understanding. Some contributions prove more significant than others, but all have potential value. The amateur observer carefully counting meteors and noting times contributes data that, combined with thousands of other observations, reveals patterns in shower activity. The professional astronomer developing models of stream evolution relies on that observational foundation to test and refine theoretical predictions. Both roles are essential. Both contribute to the shared enterprise of understanding. This democratization of participation is particularly evident in meteor astronomy, where amateur contributions remain scientifically valuable in ways that are less common in some other fields, requiring expensive equipment or specialized facilities. Anyone with clear skies and patience can observe meteors. Anyone willing to record their observations systematically can contribute data useful for scientific analysis. This accessibility is part of meteor showers' enduring appeal. They are phenomena you can observe directly, with no equipment more sophisticated than your eyes and perhaps a lawn chair. They occur predictably, allowing planning and preparation. They produce visible results, the reward for patience being the sight of meteors streaking across the sky, and they connect you, however briefly, to processes, spanning the solar system and extending back to its formation. These connections, personal and cosmic, temporal and spatial, scientific and aesthetic, are what make meteor showers special. They are not just astronomical phenomena to be observed and catalogued. They are experiences that engage multiple facets of human interest: the desire to understand, the appreciation of beauty, the connection to history, the sense of participating in something larger than individual existence. When you watch a meteor shower, all of these dimensions are present, whether consciously recognized or simply felt. The streak of light is beautiful. It is also a physical event with specific causes and consequences. It is part of a pattern that has repeated for thousands of years and will continue for thousands more. It connects you to observers throughout history who watch the same showers. It connects you to the solar system's past, to the formation of comets billions of years ago. It connects you to the present moment, to the quiet darkness and the patient watching. These connections persist even as individual meteors come and go. The experience of watching accumulates over time, each shower adding to the memory of previous showers, each meteor contributing to an overall impression that transcends any single event. Over years of observing, you build a personal relationship with these phenomena, recognizing the character of different showers, anticipating their return, remembering particularly spectacular displays. This personal history parallels the scientific history, operating at a much more compressed timescale but following similar patterns: accumulation of observations, recognition of patterns, development of expectations, occasional surprises that expand understanding. Your individual experience, modest though it may be compared to the scientific enterprise, is real and valuable. It grounds the abstract knowledge in concrete experience, making the physics and mathematics more than just formulas, but descriptions of things you have actually seen. This grounding in experience is important. Knowledge without experience can seem hollow, disconnected from reality. Experience without understanding can seem random or mystical. The combination of experience and understanding, each enriching the other, provides the most complete engagement with natural phenomena. You see the meteor and you know what it is, where it came from, how it produces light, why it appears when and where it does. This knowledge enhances rather than diminishes the experience. The mystery is not lost, but transformed into wonder at the intricacy and orderliness of natural processes. As our exploration draws to a close, this seems like the appropriate note to sound. Wonder informed by understanding, appreciation deepened by knowledge, personal experience connected to scientific framework. Meteor showers offer all of this. They are accessible to anyone willing to look up on clear nights when the streams pass by. They are comprehensible to anyone willing to learn the basic physics and geometry underlying the phenomena. They are beautiful to anyone with eyes to see and patience to watch. The invitation remains open every year as Earth makes its regular rounds through the various streams. The Quadrantids in January, the Lyrids in April, the Eta Aquariids in May, the Perseids in August, the Orionids in October, the Leonids in November, the Geminids and Ursids in December. Each has its appointed time, its characteristic behavior, its own connection to a parent comet or asteroid orbiting somewhere in the solar system. The streams are there, patient and enduring, waiting for Earth's return. The meteors will fall whether anyone watches or not. But watching connects you to the process, makes you part of the long tradition of human observation and understanding. It is a quiet activity, demanding nothing more than attention and time, offering in return a glimpse of cosmic processes playing out across the sky above you. This is what meteor showers are, what they mean, why they matter. Understanding them enriches the experience. Experiencing them makes the understanding tangible. Together, knowledge and experience create something more valuable than either alone. Genuine engagement with the natural world, informed by science but not limited to it. Grounded in observation but extended by understanding, momentary in each individual event but connected to patterns spanning deep time. Satinturu. We have now traveled through the layers of understanding meteor showers, from the basic framework through progressively deeper examination of physics, chemistry, geometry, history, and observation. The information has accumulated gradually, building a comprehensive picture of these phenomena while maintaining the calm, steady pace established at the beginning. Now, as we prepare to conclude, it is worth stepping back to consider the larger context, the place of meteor showers, within the broader cosmos and within human understanding. The solar system is vast, extending from the sun to the distant reaches of the Oort cloud, trillions of kilometers away. Within this enormous volume, countless objects orbit: planets, moons, asteroids, comets, and dust particles of all sizes. Gravity governs their motions according to laws that are simple in statement but complex in application, creating patterns of movement that can be predicted with extraordinary precision when initial conditions are known. Meteor showers represent one specific manifestation of these gravitational dynamics. A comet follows its elliptical orbit, periodically approaching the sun and releasing debris. That debris spreads into a stream following a closely related orbit. Earth, following its own orbit, periodically intersects that stream. The intersection creates visible meteors as atmospheric entry converts kinetic energy into heat and light. Every step follows necessarily from the configuration of orbits and the properties of matter. Nothing is arbitrary or capricious. Everything follows from physical law. This determinism is fundamental to science's ability to predict and explain. The Perseids occur in mid-August every year, not because of any decision or intention, but because that is when Earth's orbit crosses the orbit of debris from Comet Swift-Tuttle. The Leonids produce occasional storms not randomly, but when Earth passes through relatively fresh, dense filaments of debris from specific historical passages of Comet Tempel-Tuttle. The predictions are possible because the underlying processes are lawful and consistent. Yet within this determinism, there is room for variation and surprise. Stream structure has complexity that our models capture imperfectly. Small variations in initial conditions, in ejection velocities, in gravitational perturbations, in radiation pressure effects, can produce observable differences in shower activity. Predictions are probabilistic rather than certain, offering expected rates and timing but allowing for actual results to vary somewhat from expectations. This reflects not fundamental indeterminism, but rather the practical limitation of modeling complex systems with finite precision. The balance between predictability and uncertainty, between pattern and variation, between understanding and surprise, makes meteor science engaging. We know enough to make useful predictions. We do not know everything. Each year brings new observations that confirm or refine or occasionally overturn specific predictions while reinforcing confidence in the overall framework. This is the pattern of healthy science: strong foundation, ongoing refinement, openness to correction when observations demand it. Placing meteor showers in this larger scientific context helps clarify their significance. They are not isolated curiosities, but part of the broader study of small bodies in the solar system, of orbital dynamics, of atmospheric physics, of the history and evolution of the solar system itself. Understanding them contributes to understanding these larger topics. Models developed for meteoroid streams inform models of other debris clouds around the Sun. Techniques developed for predicting shower activity find application in assessing potential hazards from larger asteroids. Chemical analysis of meteor spectra provides constraints on the composition of cometary material and, by extension, on conditions in the early solar nebula. These connections between apparently separate topics, the way understanding in one area illuminates understanding in others, characterize mature scientific fields. Nothing stands alone. Everything connects. Meteor showers connect to comets, to atmospheric chemistry, to solar radiation, to planetary perturbations, to the formation history of the solar system. Following these connections builds a coherent picture of a universe governed by consistent physical principles operating across all scales and environments. For observers, this interconnectedness might remain largely abstract, a matter of intellectual curiosity rather than immediate practical concern. What matters most is the direct experience. Standing under a dark sky, watching meteors streak by, feeling the quiet satisfaction of observing something beautiful and rare. The scientific framework enriches this experience by providing context and meaning, but it does not replace the immediate aesthetic and emotional response. This balance between intellectual understanding and direct experience, between analysis and appreciation, is important to maintain. Science is not opposed to wonder or beauty. It provides additional dimensions of both. Knowing that a meteor is a grain of ancient dust from a comet makes it more wonderful, not less. Understanding the physics that creates the light enhances rather than diminishes appreciation for the delicate beauty of that light. Similarly, the historical connections, the recognition that you stand in a long tradition of observers extending back thousands of years, adds emotional resonance to the experience. You are doing what countless humans before you have done, watching the night sky, noting patterns, trying to make sense of what you see. The tools and the understanding have evolved dramatically, but the core experience remains recognizably similar. The link connects you not just to the cosmos, but to humanity's long engagement with it. This dual connection, to cosmic processes and to human tradition, gives meteor observing a richness that transcends simple description. You are participating in something simultaneously old and ongoing, both timeless and temporally specific, universal in its physical basis and personal in its experiential dimension. These layers of meaning, these multiple ways of engaging with the same phenomena, are part of what makes amateur astronomy generally, and meteor observing specifically, rewarding activities. The accessibility remains important. You do not need to understand all the physics to appreciate a meteor shower. You do not need to contribute to scientific databases to find value in observing. The phenomena are there for anyone who looks. The understanding is available for anyone who seeks it. Both the observation and the understanding can be pursued at whatever level suits your interest and circumstances. There is no minimum threshold of involvement, no requirement beyond willingness to spend time under dark skies and to pay attention to what happens there. This openness, this democratic accessibility, is precious and should be protected. Light pollution increasingly threatens access to dark skies, making it harder for people in developed areas to experience the night sky as humans have throughout history. This is a loss not just aesthetically, but educationally and culturally. Meteor showers and other astronomical phenomena provide direct, visceral contact with the cosmos, a reminder that Earth is part of a larger system, that the universe extends beyond human concerns and operates on scales vastly exceeding human timescales. These reminders are valuable. They provide perspective, humility, context for understanding our place in the cosmos. Losing the ability to observe the night sky easily would diminish this perspective, leaving us more isolated, more focused on immediate human affairs, less aware of the vast context within which those affairs take place. Advocating for dark sky preservation, for limiting light pollution, for ensuring that future generations can observe meteor showers and other celestial phenomena, is therefore not just about preserving observing opportunities for amateur astronomers. It is about preserving connection to the cosmos that has always been part of human experience. Looking forward, meteor science will continue to advance. Better models will improve predictions. More detailed observations will refine understanding of stream structure and evolution. Potential new showers from recently discovered comets will be predicted and confirmed. Spacecraft missions might sample meteoroid streams directly, returning particles for laboratory analysis. All of this will deepen understanding while maintaining the essential nature of the phenomena. Small particles burning up in Earth's atmosphere, creating brief flashes of light that connect present observers to ancient cosmic processes. The showers will be there. The streams will persist. The pattern will continue. Your opportunity to observe, to participate, to experience and understand remains open. Every clear night when a major shower is active offers invitation. The only requirements are willingness to go outside, to look up, to wait patiently, and to appreciate what you see. Everything else, the entire structure of understanding we have explored through this long journey, is available to support and enrich that basic experience, but is not necessary for it. You can watch the Perseids knowing nothing of the physics and have a wonderful experience. You can watch the Perseids knowing everything we have discussed and have a richer experience. The phenomena accommodate both approaches and everything in between. This flexibility, this openness to different levels of engagement, is one of their virtues. They offer something to everyone willing to look: beauty for the aesthetically inclined, patterns for the mathematically minded, connection for the historically aware, data for the scientifically curious, and simply peaceful contemplation for those seeking it. As this extended exploration concludes, the invitation remains. Go outside on the next clear night when a major shower is active. Find dark skies if possible. Allow time for your eyes to adapt. Look toward the darker parts of the sky, not directly at the radiant, but not ignoring it either. Be patient. The meteors will come. Each one will last perhaps a second. Each one will be unique. Some will be bright, some faint. Some will leave trains, some will not. Together, they will constitute an experience. Ancient dust meeting atmosphere, energy becoming light, cosmos intersecting with perception. That experience, repeated across history and geography, shared by countless observers while remaining individual and personal, is what meteor showers offer. Understanding them, knowing what they are and how they work, enhances the experience without replacing it. Knowledge and experience together create something richer than either alone. Informed wonder, educated appreciation, science and aesthetics joined. This is the state toward which we have been working throughout this journey. A place where understanding and experience reinforce each other, where factual knowledge provides context for observation, where observation makes knowledge tangible and real. If this exploration has helped move you toward that state, if the information has clarified rather than obscured, if the pace has supported rather than demanded, then the goal has been achieved. The meteor showers continue. They will be there next time Earth passes through each stream. The opportunity to observe, to appreciate, to understand, renews itself year after year. This renewal, this reliable return, this predictable recurrence is itself comforting. In a world full of change and uncertainty, the meteors fall on schedule, governed by laws that operate consistently across time and space. They will continue to fall, patient and inevitable, long after we are gone. While we are here, we can watch, we can understand, we can find meaning and beauty in these brief flashes of light. That opportunity is gift enough. Thank you for journeying through this extended exploration of meteor showers. If this has been calming, if the information has been interesting, if the pace has been comfortable, then the time has been well spent together. The universe continues its patient patterns. The comets orbit, the debris spreads, Earth turns, the meteors fall, and we, for a time, can watch and understand. If you enjoyed this exploration, consider subscribing to Nebula Nights for more calm, detailed examinations of cosmic phenomena. Each video aims to balance accurate information with peaceful delivery, providing content that engages the mind while supporting rest. The universe is vast and full of wonders. There is always more to explore, more to understand, more to appreciate. The like button supports the channel and helps others find this content. Subscribing ensures you will not miss future videos. Both actions are appreciated but never required. The content exists for you to use as you wish, for learning, for relaxation, for falling asleep, or for whatever purpose serves you best. Clear skies and peaceful rest. The meteors will be there when you are ready to watch them. Until then, may your thoughts be calm, your rest be deep, and your dreams be filled with light.